So welcome back from lunch. Hope you enjoyed it. And let's continue with the device session. So the first presentation will be given by Simone Rascuna from ST Microelectronics, and he will talk about technologies to enhance power system efficiency with silicon carbide. Yes, please.
You can hear me. So thank you for the kind introduction, and thank you for inviting me. So good afternoon to all of you. I'm really lucky because I love, let's say, happy people, and I think that after lunch you will be more happy than before. So I'm really lucky for this. So my name is Simone Rascuna. I work in ST Microelectronics since 2002, focusing first half of this time on silicon superjunction MOSFETs technology development, and the second half part focused on silicon carbide technology development. So at the end, the combination of the two is it's a perfect joint to for me, because now we are starting to develop, silicon carbide superjunction MOSFET, and we will see after on. And then I came from Catania, where our R&D and the production is based. So this is a picture of my city. So we have a beautiful sea, as you can see, and black rocks that are generated by the lava that came from the Etna volcano. So after this introduction, so let me have a look on the agenda. So we will talk about the key role of power conversion efficiency, the central role of silicon carbide. Then I will mention some strategy of ST, and we will focus on silicon carbide technology of ST, and then takeaways. So the key role of power conversion efficiency. First of all, what is the, let's say, the great change that we are looking to the how we produce energy from combustion to conversion is no more, let's say, a dream. It's a reality. If you look which kind of energy we generate in 2022 and the numbers. So I would like to start this presentation saying that we are in a real conversion, a real change on the energy production. Of course, we need to be efficient to do this, to manage this kind of energy, starting from the generation of the energy from renewable sources. Then we need to take care about the power lines and distribution, the ACC conversion. We need to be efficient also there, but also in the storage and the AC-DC conversion. And finally, also in the end application, we need to be efficient. And how we can do it? We can do it first by optimizing the existing silicon technology, like high voltage MOSFETs or IGBTs, and also use the destructive wide-bandgap technologies like silicon carbide that we talk so far, and also gallium nitride, of course, and also focusing on innovative packaging like power modules. Now, the central role of silicon carbide. You know that where high power switching is required, and also the reduction in cooling, the ratio between cost and weight add a tremendous value. So you know already, it's a matter of fact, the intrinsic property of silicon carbide, it's unique, let's say, 3 times thermal conductivity of silicon, 3 times higher band gap of silicon, and 10 times higher breakdown voltage. But if we translate the intrinsic property to the device's performances, we can see that we can reach high current density, fast switching, and a lower on resistance. And if we want to translate this to the benefits that the total system can get, we can have high temperature operation, we can have system size and weight reduction, and also switching losses. Now, if you traduce on numbers what I'm saying in the previous slide, we can have 2 sections. One is for automotive section, and the other for the industrial application. What we can achieve by using silicon carbide, we can have for automotive field, we can have a longer driving range, more than 600 kilometers of autonomy. Then we can have a faster charging, 2 times faster, and then also the car weight reduction, more or less 150, between 150 and 200 kilograms. That are it is not negligible, let's say. If you look now to the industrial application, we can have an higher efficiency of about 50%, lower total cost of ownership 20% more or less, and the average size reduction of about 50% again. Now, let's spend some words on the strategy of ST. First of all, our strategy is based on the fact that we have more than 25 years of experience focusing our activity on silicon carbide. Catania was the Power Electronic Competence Center, and fortunately I was born in Catania, so I'm really a lucky guy. And we started a strong collaboration with the National Council of Research and the university. So everything started in 1996, and then we achieved many milestones, let's say, and this has to be updated, slide that to be updated because it finished in 2022 when a first 150 millimeters ingot was came out from Catania facility. Another strategy that ST is putting in place is working a lot on package technology, because we understood the value of investing of new package. So we cannot let's say focus our attention only on the front end sides, but we need to have a big effort also on the package and the back side. We are going to have a flexible approach covering packages, modules, and dies. So everything starts from the ingot, then the substrate, and then the devices on the wafers. Then we can have single devices, so we can put each dies in different packages, providing many products to the customers, or have many devices in a single package or modules. We are a vertical integration fab to supply the chain resilience. Indeed, we start from the raw material now, and we can have our silicon carbide ingot, so the substrate. Then we have the manufacturing of the silicon carbide dies, and then, as I said before, discretes and modules, and the finished product. And this is feasible because we have in Norrköping the silicon carbide substrate R&D plant. So we produce 150 millimeters substrate there, and we have now a quality, industrial quality, and yields also on 200 millimeter wafers. And maybe you know, or I'm going to tell you that in Catania we built a new silicon carbide integrated plant. So we do more or less everything inside these facilities. That was a pilot production last year, starting from 150 millimeter substrate, and we do also the epitaxy. And in the next future, we have in mind to convert everything to be sustainable with 200 millimeters wafers. Now, there is also another strategy, of course, of ST that is expanding the silicon carbide device manufacturing. And this is thanks to, in front end, we can, let's say, increase the front end by using Catania site and Singapore, and the back side using our plant in Buskura and Shenzhen. The goal is to have, using Catania and Singapore, so for the front end manufacturing, the forecast for 2025 to have a capacity that is more than double the capacity that we had in 2022. This was already mentioned in one of the previous of this morning, I think, talk. So we did a joint venture with Sanan Optoelectronics. This is very important because in this let's say it's important to support the demand that is rising for car electrification and also for industrial power directly in China. The market, it's huge, and it was important for ST to have a base also directly in China to serve the many customers that we recognize and we have in China. And then Sanan will have separately a 200 millimeter silicon carbide substrate plant in the next future. Now another strategy is to use a new approach on the substrate. Indeed, we are looking to use Soitec SmartSiC. That the difference. So now we conventionally use 4HSSE, so monocrystalline substrate, and we use it to do our devices. But there is another approach that is this smart cut approach, in which there is a bulk of very low resistivity substrate that is a polycrystalline, and we put on top Soitec put a thin 4HSSE substrate, so monocrystalline, on top that is ready for the epi growth. But the resistivity, the lowering of resistivity gave us many benefits. First of all, the benefits, the most important benefits, that we can increase the number of producible wafers. So the second is that we can get benefits on the reduction of the substrate resistivity. I put here some experimental data demonstrating that, made on silicon carbide diode 650 volts. So as you can see here in this chart, we have the forward current in the y-axis and the forward voltage in the x-axis. And this is a typical IV curve. The black field points the standard characteristics IV of the standard devices. And then on the, let's say, white field points, we have the new IV curves coming from the use of SmartSiC as substrate. You can see the benefits, and we did also we fit very well with the model by considering only the difference between the two resistivity from a SmartSiC and a normal substrate, monocrystalline. So in the normal devices, you can see here in the pie chart, we have the three principal main component of the resistance, that are the substrate resistance, the contact resistance, and the drift resistance. In the conventional devices, the substrate resistance has a weight of more or less 47%. If you look what we can reduce here, it's we are going down to 10%. So and the benefits it's quite clear. Now, if we focus our attention on technologies, what we can discover here is which is the evolution of our technology on silicon carbide diodes. Okay, in this chart on the left is we are focusing on 650 volts devices. So in the x-axis we have the maximum value of VF at E0, so nominal current, and room temperature, and in the y-axis we have the ratio between IFSM, so that is the maximum current that the device sustain at surge mode, and the IF is the nominal current of the devices. So this point and this point, so the blue and the red, are the devices that we have actually in the market. So it is a so-called low voltage 650 volts devices, and another one that is an high ruggedness, let's say, devices at IFSM test. So now what we are going to put in the market is a new devices that combine the two benefits. So we will have directly one single product or technology that is a low voltages and very high rugged one in terms of IFSM. And the same, more or less, in 1200 volts, we have already a good positioning in VF, so we are not going to go down in VF, but we are just increasing the robustness of our devices. Let's have a look also on silicon carbide planar MOSFETs, so we will see the evolution. So here I put a chart which we have the specific resistance versus the generation, so from generation 2 to generation 5, in which we are progressively decreasing the gate source voltages. And you can see here the benefits in terms of reduction of specific resistance versus the different generation. You can see that we have benefits at room temperature. What is very important is the benefits that we have at 175 degrees C. From the first generation to the last generation, we have a jump of more or less 50% of gain. And this is for 650 volts, and you can see that we can have more or less the same chart for 1200 volts, and here the benefits is even higher, close to 56% at 175 degrees C. What's next? Well, ST is investing a lot on what I said previously when I start my talk in superjunction silicon carbide MOSFETs. You know that we have many components for the total resistance of the devices. We are focusing on addressing and attack the AP component by using the superjunction concept, reusing in some way the multi-drain approach that we use and we are using on silicon MOSFETs. This is will bring a big benefit. Also, because if we are reducing the resistance of the AP, you can imagine, you can see that the substrate resistance became the weight is higher, will be higher. So again, the approach of thinning of the wafers or the use of SmartSiC will be an adding value, let's say. Here are some simulation what we can get by moving from a standard planar device to a superjunction column, and you can see here that you can have again a reduction at 175 degrees C of 20% at 650 volts, and again a reduction of the resistance, let's say the specific resistance of about 60% on 1.2 kilovolts. Okay, this is my, I think I am in time, right? Am I in time? Yeah? Yeah. I start on 1:30, yes. So some takeaways. So silicon carbide, sorry? Okay, good. So silicon carbide is key in power conversion efficiency. The demand for silicon carbide is growing very fast to support the electrification of the cars, so in automotive, but also in the industrial market. ST is investing to support the market needs with a vertical integration manufacturing strategy. Okay, we are going to focusing and invest on package solutions. That is very crucial, let's say, very important. We can say that we have a very good silicon carbide MOSFETs planar technology, and I would like to finish my talk with a comment that I was thinking before. It is not written here. The fact that if you really want to convert all the car in the world to be electrical vehicle, the number of silicon carbide 8-inch wafers that we need to supply is huge. So huge that at the end, I can say in some way there is will be no more competition between the companies, because the quantity of the wafers is so huge that all the companies have room to serve and to have their space in the market. The point is that if you want to really to do this conversion, we need to also to be consistent and coherent, let's say. We must be green company. This is the reason why ST has the great ambition to reach the carbon neutrality by 2027. Thank you very much for your attention.
Thank you very much. So we're a little bit over time, but we have like probably 2 questions. Yes, Andrei.
What do you actually mean saying about gray?
Multi-drain is the approach that we're using on silicon. This means that we have a multi-growth of epi. So we do a first epi on the substrate, we do the implantation, then we grow epi implantation, and so you can have the P column done by this process.
A question here. Thank you for your very nice talk, describing everything thoroughly. So my question is for the super junction that you're doing, the epi, basically when you implant, you go about maybe 0.7, 0.8 microns, right? And you try to do a 12 micron or 10 micron device, right? You need all these implantations and regrowth. So from a labor intensity cost perspective, you will get some advantage in resistance, but is it worth?
Yeah. Interesting question, Victor. So thank you for your question. I cannot say everything on the process, but I can give you only let's say an insight. I mean, we are going to do thicker epi grow, not the one that you mentioned. So yeah, right. Thick one, and the implantation is the optimized one to cover this thickness. So it will be convenient at the end of the day.
Okay, so part two, because I'm only allowed one question. Part two, with the Soitec, right?
We're out of time.
It's the wafer now becomes opaque, not transparent as before.
Yeah.
How does it change the fabrication you're doing? Because now all the optical type of measurements, inspections, CD SEMs need to go back to the silicon opaque type of equipment versus the the equipment for the transparent.
Yeah,
Is that complicated or?
Yes, you are right. But at the end, it was more complicated to do the opposite. From silicon to silicon carbide was a nightmare, and we did it. We are seeing that to do the opposite at the end, since maybe because we also develop knowledge and we know how to manage, it's more easy now.
Thank you.
Thank you to you.
Thank you.
Thank you. Thank you again.
Let's move to the next speaker. It will be given by my colleague from Coherent, Francis Chai. He will talk about ruggedness and cost efficiency of silicon carbide MOSFET technology.
Good afternoon, everybody. My name is Francis, and we have the device group, transistor design group here in Kista in Sweden. And myself, I'm based in the US currently. Let's see. Sorry, do I do this? Oh, okay. Okay, first slide, a few words about the company. The company is well known for material side, actually. So everybody know we're a substrate provider, and the company is formed in 1971. And we have 26,000 employees worldwide, and we have 2,400 people in research and development. And we own 3,000 patents today. And we're now trying to be vertically integrated, which means we not only would cover device, but up the food chain in terms of transistor manufacturing, as well as module and system solutions. And we're traded. New York Stock Exchange, COHR is a symbol. The revenue last year is $5.2 billion. And the market size is about 64 billion. So we are under 10% with lots of opportunities. We have 126 locations all over the world in 24 countries. And then a few information on the transistor group. We have the power transistor R&D center here in Kista, Sweden. And I came here a few times to know how to say not Kista, but Kista. And we have advanced epitaxy here. We do high voltage epi growth and regrowth, and also we can have multi-layer epi. And we have 150 millimeter, 200 millimeter in production. And we do the MOSFET design as well as diode here. But we're fabless, so we manufacture at a foundry. We are ISO 9001 certified. And we have colleagues which work on the module. And we're based in Munich area in Germany. And we are focusing on automotive market and also some aviation. And the module prototype will be done in Munich, but we also have mass production in Asia. And from quality point of view, we're ISO 9001 certified. We have a class 10,000 clean room there. And then we have aerospace certification. And in general, our vision is to be vertically integrated. That's easy to say, but I was sitting in Professor Hans-Peter's tutorial. Myself, I have the background mostly in RF. So I see in the audience, there are only a few spring chickens now. So any of us old enough will remember what the cell phone looked like. So I got out of school 1997. At the time, we work on 0.25 quarter micron CMOS technology. And very few people would have cell phone, right? And then what happened is, I remember Bill Clinton was in office, and we have a spectrum that's, say, around 1-2 gigahertz. That's owned by United States government, also higher frequencies. And he auctioned it off. And at the time, silicon technology was ready for something big. So before that, the mobile phone concept like that is always huge, as you know. So the whole receiver chain, each, like LNA would be one element. And then you go to VCO will be one element. So it's huge. The reliability is rather poor. But at the time, if you look at the technology, it's ready, and the government allowed the spectrum to be used. So suddenly you see this revolution. I remember every conference we were talking about Bluetooth. We're talking about GSM. So suddenly the whole receiver chain is now almost one chip, all the way to DAAD converter. So the integration level is very high now. It's unbelievable. The time was just right. Now I've been working on power electronics since 2015. I work on some silicon MOSFET, silicon carbide MOSFET. But when I first got into the field, I felt kind of depressed because you look at the back-end cross-section, it looks very, very ugly, right? Compared with a CMOS process that has 9 layers of metal or more. It's very beautiful, but those small signal MOSFET doesn't have any power. It's like you have a little sports car, you can tow a trailer with 3 horses in it. So power electronics with time, I understand it, but advancement, I also agree with Professor Guo, is very, very slow. It seems like the transistor part works, but the packaging part and the supporting structure is not there. That's packaging or thermal or gate driving. It's not there to make the integration level as high as or efficiency as high as the RF industry have produced. So I agree. So our vision for vertical integration is we hope to be able to provide a system solution that's efficient, and really has a breakthrough instead of just offering a few modules type of thing. So that's our vision. So to jump into some technical discussions of our MOSFET, we are ISiCPEAW rated at junction temperature of 200 degrees C. And we rated at a high temperature because then at use condition, it will be much easier. And I'll show data that we have robust gate oxide, and we have ruggedness in hard switching. And then we have also competitive cost. And the first slide here in the technical section is about the gate oxide. So for our gate oxide, we did reliability modeling early on while doing process improvement. So on the left chart, you can see a Weibull plot, a cumulative probability of Weibull. Those different colors symbolize data with combination of different electric field, which is the gate bias, and junction temperature. And because of that, we were able to have a reliability model that's a function of electric field as well as temperature. And that allows us to project acceleration factor. So when we rate at 200 degrees C, all the conditions at use becomes simple. So in the meantime, the manufacturing needs to be cleaned up because, as you know, you can have a very good design, but at the end of the day, any defectivity will kill the lifetime. Because in reality, in real life, doping is not the only factor that determines your breakdown voltage, but the weakest point. So we clean up the manufacturing. You can see the Weibull plot doesn't have infant mortality there, and also the population has very good breakdown voltage. The slope on the Weibull plot looks very good, and the rate at 200 degrees C. I mark on the right-hand chart the acceleration factor at a typical automotive temperature of 120 degrees C and 175 and 75 degrees C. Those are the three main ones in the mission profile. That becomes very simple. At 175 degrees C, for example, the lifetime will be 2.7 times higher than the 200 degrees C temperature. And at this use condition, we would have more than 400 years of lifetime. And so in general, this ruggedness make the transistor reliable in the field. And then talking about the ruggedness, on this page, I'm showing the avalanche ruggedness. This is a very typical clamping inductive test. And in the test, we know if the inductor is charged up to a steady state current. If the transistor is suddenly turned off, the inductor doesn't like that. So it will try to keep the current going by pulling the drain voltage high. And if this event is happening by pulling current out of the termination region, then we know it will be lethal. But the transistor is designed such that the avalanche is happening mostly in the active region. So the heat can be spread out. The event then becomes sustainable. So for this particular device, 20 milliohm device, we see single pulse avalanche energy of 3.6 joule with 8 millihenry of inductor value. And we checked this avalanche energy across different device types. On this chart, I'm showing the normalized avalanche energy. So basically, you take the total energy divided by the die size. And on this chart, the x-axis, I'm showing different voltage node. You can see 1.2 and 1.77 kV. And we also have different die sizes there as marked on the RDS(on) value. Meanwhile, there's a mixture of different color in the data point that symbolizes different die thicknesses. And we have different overseas assemblies, as well as the different molding compound material. You can see everybody is pretty uniform, regardless of all those variants showing the chart. So this is a tally of the failures we have observed as we clean up the process on our transistor. And on the right-hand side, I'm showing different current where the transistor got killed. And also there's a tally of the energy. And overall, there's no correlation of the fatality location to energy or current. It always happens in the active area. That shows that the transistor is optimally designed. And the termination region is robust enough to sustain the voltage, but the event is happening mostly, avalanche current is mostly supplied by the active area. And the next is the short circuit withstand. We know that for a power converter, we would have to have a basic requirement for this for safety. Generally, it should be higher than 3 microseconds. It's a very thermally intense event because the drain voltage of the transistor will be high and the drain current will be high at the same time. So on the left-hand side is a typical transient of the short circuit event. And the drain current went to as high as 570 amp for a 20 milliohm transistor with breakdown voltage of 1.2 kV. And as you can see, the total short circuit withstand time is above 6 microseconds. And we do check this as material comes out of our line by sampling. And generally, for this die size, you can see the distribution is quite nice. It's always above 5 microseconds. And we have provided our automotive customers also with samples. And the feedback we get is they subject the transistor to 4,000 cycles of repeated short circuit withstand test with a current density of 4 kiloamp per unit area in centimeter square. And the voltage is 850 volt. And the turn-on time for each pulse is 2 microseconds at the frequency of 50 hertz. And our device survived with no significant change in the electrical characteristic, while the competition device died of gate rupture. So this is the last two slides with data is about the efficiency in the design, basically the design for low cost. So on this slide, I discussed the active area over die area ratio. We all know that to make a 5-volt MOSFET is a lot easier than or 50 volt than 1200 volt MOSFET because you need to block all those voltages. So we also know that from physics that voltage is a spatial integration of the voltage. So you simply cannot work around physics. You need to provide a space to distribute the electric field so the voltage will add up. So as a result, the edge termination will occupy space. So this is a plot of how much area is basically spent on the edge termination. For our transistor, you can see I have various different vendors in different color. Our transistor is the green diamond. And also there are two types of technologies. The planar one is the empty diamond, and then the filled circle is the trench technology. And for our transistor, you can see the active area has a high ratio to the total die size, which is plotted on x-axis. And a lot of competition, they fall below. That means they spend more area in the edge termination to manage high voltages than our transistor. And for the trench technology, we know that we need to have we want to have high packing density for cost reasons. But at the end of the day, you still need to block voltage. So some older trench technology, and the red data point is a very well-known manufacturer. They fall below in this category. So this is about edge termination. And then the next one is the overall cost. So on this chart, I'm plotting the specific resistance. This is based on total die size, not just the active area, because we believe the specific resistance value should include the total cost, which is the edge termination also. And on the x-axis, I'm plotting the current density, also the total current average to total die size at 175 degrees C. And again, there are different colors here. Our transistor is the color green, and the two different technologies, planar again is diamond, circle again is trench. As you can see, there are, for example, two different blue points here. And the two blue points are the two different generations of a well-known company, trench technology. You can see that there's significant increase in the packing density of channel. However, the current density is not increasing as much. So at the end of the day, if I specify my module for a certain current capability, the newer generation actually would need more die size in order to support that current. So the current density is important. And another thing is you can notice that there's overlap now. There's some, the pointer is not showing up very well, but at the current density of 7 amp, you can see there's planar technology now that's as good as trench. So this is very important because trench technology we know overall is a lot more expensive to develop. And also it's trickier in terms of reliability and the performance. So in order for planar to be good, you need to pack it enough. And then without such cost, you can reach the same kind of cost in terms of packing density. So it's getting really competitive. For us, currently we don't have a trench manufacturing. We're looking into it. But our current planar technology, because we're rated at 200 degrees C, the gate oxide is reliable enough at 200 degrees C, so we can push the packing density more. And that gives us leadership in the specific resistance as well as in current density. And so as a result, if I have a module that requires current capability, then we can still have economic die size, not only from the ROM point of view. And then this is the last two slides. The first part of the last section is I'll leave you with the impression of the die that we'll be offering in the coming 2 years. And all of them will be ISiCPEAW 101 certified, and also they will be industrially certified also. And we not only offer in typical plastic package, we also offer in bare die form. And the last slide, I leave you with the impression of our upcoming module offering. We will be at PCIM. We will have a booth, so you're welcome to visit. And finally, summary. So I discussed our MOSFET transistor. We are very young compared with some of the very, very experienced veteran companies in the field. But we have achieved the ISiCPEAW 101 qualification with green mold compound. We're rated at 200 degrees C. That gives us advantage in reliability, a little bit in the current cost also. And we have robust gate oxide. Because of the high temperature rating, we have more than 400 years of lifetime with typical use conditions in automotive. Good short circuit and withstand, stable in manufacturing from lot to lot, good avalanche ruggedness, very consistent among the portfolio of offering. And we have a cost competitive design. That's the end of my presentation. Thank you.
Thank you. We have time for 2 short questions. Yeah. My microphone, please.
It's very interesting that you have made so much progress. I have a question about this short circuit. You have shown that you have a comparatively long time, and you can repeat it several thousand times. But I'm interested, what did you estimate the temperature during one event? Because it is also maybe a power cycle to a very high temperature.
Sure.
And I'm afraid of an effect to other reliability aspects of the device. Of course, you have shown that it survives, but
sure.
I want to know the temperature.
Sure, that I think we would have data on it because the power dissipation through the event is known. So the temperature, I think we have data on it, which I don't have it in my head, unfortunately. But it is a very high dissipating event. So gate oxide robustness is important, but it's definitely way beyond the rated temperature. So we'll basically it's like that video game, you keep getting hit, you see the life bar will go down, that's for sure. Anything else?
Okay, Victor.
Thanks for your presentation. I looked at your edge termination where you say you're very space efficient.
Yeah.
Meaning that the extent of your edge termination is relatively small.
Smaller, yeah.
But my question is, what is your efficiency? How close does your edge termination get to the ideal value? Because the shorter you make the edge termination, right, the lower you will be able to get to the ideal value. The longer you make the edge termination,
ideal value, you mean breakdown voltage?
The breakdown voltage of the drift layer based on its doping thickness. You have a value there. How close do you get to that?
Yeah, our breakdown voltage is competitive with all the vendors out there. So it's not lower. The leakage characteristic when you do the drain voltage sweep up is also very similar.
Okay.
So it's I would say the design is different, which is proprietary.
Okay.
Yeah. Indeed, the physics you cannot get around. You have to, when you deplete the electric field, the spatial integration will sum up to the voltage. That part is the same. Everybody has to work with that. But because of the design, we can have the same breakdown voltage but less space.
Okay.
Yeah.
All right. Thank you.
Thank you. So we move to the next speaker now. The next talk will be about gallium nitride. That will be given by Dilde Shaud-Hari from ISiCPEAW. And the title is Power Gun Technology for Automotive and High Current Applications. The stage is yours, please.
Oh, thank you. Good afternoon, ladies and gentlemen. So I'm from ISiCPEAW, and I'll be sharing with you some of the high current carrying capability of the ISiCPEAW, the GaN that we are working on. Invariably, you are introduced with that the GaN invariably is for low power, and silicon carbide is for high power. But here, I'll share some of the experiment that we have done to share you that the GaN is also capable of high current. Right, just to introduce our company, ISiCPEAW, we produce over 100 billion products every year. So, and about 9.4% global market share that we have got, over 15,000 employees, and our last year's revenue is just there. I think this is a familiar picture, but only the power and the frequency scales varies between people whom you are talking to. Because if you look at this one, it shows that the GaN is capable of in excess of 100 kilowatt power capability. And that's what we have got our in-house experiment that we have done with some of the devices that we have produced in-house, and that's actually gave those kind of capability. Right, just to refresh why the GaN is so much better in the journey for a higher efficiency and better power conversion. Obviously, we know that the bandgap, the critical electric field, the electron mobility in particular, most of the GaN devices are now based on high electron mobility transistor. And so the mobility is not only very high at room temperature, actually quite high at high temperature as well, which is one of the benefit of this one, and also the saturation velocity is quite high. What it means that the carrier need to travel much shorter distance, and as a consequence, high speed, shorter distance, and that what we get the benefit of high speed switching benefit by the GaN devices. And obviously, the EPI is quite critical part of the GaN device manufacturing. And unlike silicon devices where you can actually get the EPI and then your process has got significant contribution, but in the GaN devices, actually the EPI also significant part of your application and the switching. So you cannot ignore the EPI. That's why every vendor's GaN devices are different and their performance are different. Obviously, GaN is a very, very fast device, as all our previous presenters already highlighted. You cannot just plug and play with GaN devices, replace the silicon or the IGBT and put the GaN device. It's not going to work because GaN device is so fast that any inductance en route will cause problem. So it's no point having a best of your semiconductor without the complementary best packaging to go with it. So that's the reason we brought what is called all-clip, copper clip packaging, so that the inductance of the package is actually complemented with the GaN device in such a way that you actually get a lot less ringing, especially when you are running at 100 amps, 150 amps. Imagine what is your half Li square loss can cause. And you can have lots of problem if we are not careful making the environment around the GaN device suitable for that purpose. Obviously, GaN is very high efficiency, and GaN, because it's based on GaN on silicon substrate, it is very easy to scalable. You can use most of the silicon fabs to do this one, as we do as well. And obviously, we are on the way to bring the automotive qualified power GaN devices. We have got quite a few released product for industrial applications, but the automotive qualification is ongoing. Our business model is we always bring the products for the consumer and industrial application first, and about a year or 2 years later, all our products usually we convert into automotive grade. And in the meantime, we get all the experience of the products that's being used in the field, and we have got lots of information from there. And there are obviously two variants of GaN devices. One is Cascode, another one is E-mode. E-mode device is obviously single die device, and Cascode is actually 2-die device. And if you look at the oops, sorry. So we have got a low voltage super junction device. I don't know how to in there. No. Oh, sorry, in this. Which one is the?
This way.
No, I want the marker.
Marker.
This one?
Yes.
All right.
Yes.
Okay. Yeah. So if you look at this one, there are 2 die. Here, this is actually a low voltage super junction based in 30 volt. And this is actually quite complementary to run this device. And this one has got some special quality that usually like, if you've got a split gate technology, you cannot use it for the Cascode devices. And the super junction devices has got a special certain property that actually complementary and perfectly match to our HAMT design, so that this two works perfectly. And because of this one, and as you know, I don't know that in the Cascode design, the D mode, you can actually increase the aluminum concentration quite significantly compared to your E mode devices, which means that your specific radiation for your D mode device is significantly lower compared to the specific radiation of the E mode devices, which enable the D mode or the Cascode devices to run at a higher current. So this is one of the things actually we see. And also obviously from the noisy environment, for the purpose of the robustness, the Cascode devices has got a very high threshold voltage. So the shoot through or the undue turn on of the devices is less probable on this one, but obviously E-mode devices has got some problem. because the E-mode threshold voltage is much lower compared to the cascode that you can make. So these are the two, but that's why we position the cascode and the E-mode devices for the lower power and the higher power application. So this one is just a coexistence of the low power and high power. Oh, no, it's okay. So I'll move into the few fundamental properties that allow the GaN devices to give the highest possible efficiency. One of them is the DVDT and DIDT. And we have done some experience comparing our 30 milliohm device compared to some of the silicon carbide. As you can see, as the current started increasing, the turn-off losses actually doesn't increase. While in the silicon carbide, actually turn-off losses varies quite significantly, which makes it quite suitable for even at high temperature, these devices. And if you look closely, you can see the highest DIDT and the highest DVDT, despite around 6 ohm gate resistance compared to 2.5, 1.8, or 0, and the GaN is actually faster device. And we also did the soft switching, and where you can see that the green line, where our GaN devices based on the cascode technology actually shows a very low power losses. The other is the third quadrant loss compared to silicon carbide or the E-mode devices, actually much lower. You can see about 1.3 volt at 20 amp comparing one device. And where the GaN, see the E-mode devices and also the cascode has got a much higher third quadrant voltage, which sometimes limits. If you're running at high power, then you'll not be able to run it for higher frequency. But the cascode devices are more capable of doing that. Obviously, QRR is one area. Another area is the one we all are very familiar with. The silicon carbide is very low very high thermal conductivity, right? And so thermal resistance for the silicon carbide is actually quite low. And this is actually valid for room temperature. As the temperature increases, actually silicon carbide thermal conductivity starts going down. But once you start doping the silicon carbide, actually thermal conductivity goes down even faster. So if you look at these two graphs, one is the top one is undoped and the bottom one is the dope. And you can see that the dotted line is actually 175 degree, where the silicon and the silicon carbide thermal conductivity it's not much difference between them. So this is one of the area we invariably do not notice that, but we are quite concentrated on the room temperature one. This is just one of the things that just expanded. So as I mentioned, the cascode technology is based on all copper clip, which actually helps not only on the inductance, it also helps actually taking the heat away efficiently from the bottom and the top on both sides. And it has the option for both side cooling, top side and bottom side cooling. And we have got these devices. You can see on the top right-hand corner, these copper clips based technology and the devices that we make. Obviously, there are few power conversion topologies. I'll just move that one. And one of the key areas for the high power application is to have a dedicated Kelvin sense pin, because that makes a big difference that we have observed. So Kelvin sense need to be really integrated. But if it is a low power, you are okay without it. This is one of the collaboration we are working with, making the GaN-based module on the cascode devices. And this one is capable of about 500 amps, 650 volt. Obviously, this is based for the 400 volt platform. And this is one of the things we're trying to bring, where higher power application. And this is just the internal structure of the GaN device that I'll be sharing some experimental results. And you can see, obviously, there it has got a dedicated Kelvin sense and all the inductances, and it's actually less than 2 nanohenry. It's actually about 1.2 nanohenry. Yeah, this is just to give you some the specification: 650 volt, 219 at room temperature, and 5.6 million. This particular die that I'll be sharing the results with you, and at a high temperature it's 13 million. So this is, you can see that there is a 500 volt, the red line, and also 150 amps. We have run this one, and with a very small snubber, actually, it's the waveforms are quite smooth, and we are quite impressed with these high current results that we have managed to achieve on our discrete devices. And this is not the largest device, but still, this is quite capable device. And this one is versus temperature. As I mentioned, the GaN devices is one of the technology that actually doesn't suffer as the temperature actually goes up. The mobility is still quite fast enough to produce a very low power losses even at high temperature. It doesn't suffer like in IGBT, you have got the minority carrier tail, or the at high temperature, the lower mobility. None of those actually happens on the GaN. So you can see that at 150 degree, the waveforms are almost identical. Yeah, one of the questions comes that, oh, you use silicon devices in your GaN cascode. So you have got QRR, but if they scale, invariably you forget, because a 30 volt silicon device QRR is actually about 10 nanocoulomb. And if a 600 volt silicon device QRR is about 3000 nanocoulomb. So there is a huge difference. So a low voltage silicon doesn't suffer from that. And that's actually the demonstration of that one. Even at high temperature, you can see that the silicon device internally integrated with the device actually has got no problem with this one. And turn-on loss obviously is dominated by the gate resistance. We control the slew rate, but on the turn-off losses, you can see independent of current. You can see it's a very low turn-off losses. And also you can actually control the DVDT more or less like for the traction inverter of the order of about 20 volt per nanosecond. And turn on and turn off, you can actually control with this one. So these are quite high current measurement that we have done. And then we have done some continuous current measurement, and it actually with the cold plate and things, this is just a confirmation of the QSS doesn't suffer as much. So the continuous switching we have done with this one, and I just go to the results. So you can see that at different frequencies, we actually run a maximum power of these devices, converting from 400 to 230 volt buck converter, half bridge. And you can see that this device is capable of quite significant power level. And so this is one of the area that I believe that the GaN has got a future once we're working for the, especially for the high power DC-DC, like 100 kilowatt, or the high power traction inverter. And we're also working on the multi-level, where the 650 volt GaN device can perform quite efficiently for the multi-level. There are lots of interest out of that one, and where even the discrete devices can be used. Like two of these in parallel can have a huge power capability. And this is just showing the switching waveform for the hard switching and the soft switching. And we have actually stressed it much higher just to see that whether it goes out of the range. But it actually did quite well on that one. Right, just quickly, just summarizing that the fast switching results on the 7 million or the 5.6 million device tested up to 150 and 500 volt. And we believe this one actually demonstrates that the GaN is suitable for using at a high power applications as well, not only for the low power. With this one, I'll stop here. Thank you very much.
Thank you. So, questions from the audience? Victor?
Victor.
So what voltage ratings?
650 volt.
How far up do you plan to go? What's your strategic view of?
Actually, we managed to go up to 900 volt. Even though the leakage at 1100 is still quite low, but obviously you know that if you are biasing your GaN devices at very high voltage, it becomes insulated. It doesn't switch anymore. So that's actually more like academic. Yes. Obviously, you know that because of the stress from the silicon substrate, it is impossible to go to 1200 volt. But obviously, there are other substrate actually enabled us to go beyond 1200. Yeah, like a Sapphire or the QST or the other. But silicon is still struggling.
So you're focusing on the up to 900 volt market for now?
At the moment, yes.
Okay, thank you.
If we want to go to 1200, it will be something else. Yeah.
Thank you.
No problem. Then it defeats the purpose. It will be very expensive. Silicon carbide is already used for the RF. Our RF colleagues can say that, yes, silicon carbide substrate with RF obviously does give significantly higher gigahertz compared to the GaN on silicon, almost more than double, right? So yeah, silicon carbide substrate has got its value, definitely. And GaN on GaN, another aspect. But we probably will lose the high electron mobility transistor aspect.
Thank you so much for the nice presentation. I have a question regarding that you told that the gallium nitride have high current capability. How much maximum current it can bear with your GaN device and how much power it can have as compared.
Right, obviously, this particular one of our current latest generation gave 5.6 million, right? And then we have got a plan that the same device can go down to say around 3 million. Yeah, if you can improve all the process and the other aspects, and which means that you can go higher current is the power, current density, right? As long as you maintain the current density, you can make it really high current. One of the advantage of GaN, Victor already highlighted in his presentation, then the silicon carbide has got a very high defectivity. So the large die silicon carbide is comes with a huge cost of yield, but the GaN has got actually significantly better yield. Even this one is a significantly larger die compared to any silicon carbide devices, but it has got very high yield. So this is one of the advantages. So higher current is not the limit.
Yeah, we have no time for more questions. So thank you very much.
Okay.
Let's move forward. Next talk will be also about gallium nitride devices, and it will be given by Christian Gasparini from InnoScience. Please.
So test. Okay, right button. So thank you everybody for being here, and thanks for the invitation. In my talk, I'm gonna go through how to use GaN power devices to reduce size, increase performance, and lowering system cost for overall power conversion systems. And I guess that's the other direction. Okay. So let's start from this, set up the scene where we stand with GaN. And I'm using this nice report again from Iole that gives so good overview on how the market is evolving and where do we start. This is a report from last year, and you can see the starting point in 2022 for different market segments, the most important market segments, so the market overall. And we are talking about revenue or cost of power devices in GaN technology. So the good news is that all the market segments are growing very steeply. And the even better news is that some of them are growing even more. So the market is going from $185 million 2022 into exceeding in 2028 $2 billion. So if you look at this pink-orange circle here, that's the biggest one, which is the consumer market, and it's exceeding more than half of the total in this time scale. But also other markets like industrial and especially automotive will be a game changer for GaN. So like growing at 100% and more compound per year. So today, we have already many companies that are using GaN in new and existing projects because of small system size, because of higher power density, because higher efficiency, but also to make the system cheaper. That's a very important matter as well. These are some examples. We are thinking about, of course, chargers, but also power converters of different sizes, of course, to be very compact, as much as we can. And question, where do we stand with InnoScience in all this? Just to give an example, as from July last year, we have more than 300 million devices shipped from the inception of the company. And if you look at the latest reports, we have passed from about 1/4 of the market share in 2022 into almost 1/3 in 2023 and growing. So some important factors that we have to consider when we think about making a new technology or a modern technology industrialized. So to make it real, to make products with it. The first matter that we look at is performance, of course. Is a new technology making something better of the existing product? Then, of course, it has to be reliable. Nobody wants to put in the market a new technology having the risk that it doesn't work or you have too many returns that backlashes your success in the market. And together with that, people, engineers, developers, have to understand how to better exploit this technology. So it has to be understood. The other important factor is the technology has to be available. Having a perfect technology which is not immediately usable by companies is a lower, let's say, interest, of course. And the other part is price. So, of course, it has to be usable in the market, it has to have a right cost. And why not also processes that are standardized. Here the image shows package, but it's a more general concept that we think of. So talking about performance, it's complicated because there are so many parameters that we can think of. But one thing that can really simplify the way that we look at devices in the market and we compare apples to apples is to use some figure of merit. Talking about switching systems, power converters, there are two main statuses that we think of. So it's the static dissipation, when you have current flowing to the device. So the iron is the first parameter that has an impact on that. And then the dynamic dissipation, which is proportional to the total gate charge of your transistor. So you combine these two together and you have this iron QG, which is used to make this first benchmark that you can see here. Yes. So we take several best-in-class silicon superjunction FET that you can buy in the market. And we take our INOGAN, so our discrete E-mode transistor. And when plotting the Heron Gougy over different voltage or around across the entire range from 700 volt to 30 volt, we see that we are in average 10 times better for this Heron Gougy. Meaning that you can go into higher frequency and reducing the size of your passives, and also reduce your total cost for your system. Now, I want to point out that when you think about increasing the frequency, it doesn't have to be extreme. So you don't have to go into megahertz or tens of megahertz. You can, of course, but even if you use a small factor, like the factor of 2, you can already decrease your housing, your heatsink, and the total cost by lower volume of your components. For example, take this image of a flyback transformer. By doubling the frequency, you have a volume reduction of 36%. And using a frequency which is not that extreme to handle, quite straightforward. So reliability. So GaN is a modern technology, but it's not really new. So it has been studied for more than 20 years. So there is a lot of literacy, a lot of material, a lot of studies that can be used and should be used to understand how reliable is the device today. And what we do at InnoScience, of course, we need to follow the JEDEC standard, so the same standard for any power device, but we also do more. So specific testing for GaN and qualification for GaN, and also extra failure test, so time to failure for both the driving part and also the drain part. Just some graphics on how this can be partitioned, and just as a reference. Now, to give you some concrete feeling. So talking about an important matter in power converters, this is the transient reliability, so against spikes and over voltage. Silicon parts have an avalanche rating, but GaN devices do not have avalanche as technology. So how can we compare and understand where we can stretch it if needed? So let's look at this chart. When we talk about rating, in general, so you have, here is an example, so 700 volts. We take the red line here is a silicon device. When you exceed the 700 volt, you go into avalanche breakdown, and then your device is destroyed if you're not limiting the current and the power. GaN devices do like that. So they do not have avalanche, but they follow this kind of curve. So the IDSS, the leakage, and then the current flow into the drain at the device turned off increases, and then goes into destruction if it is exceeded by too much. So a time-dependent breakdown. The way that we specify in our data sheets is the following. So you have the rating, so the VDS max, like 700 volt, which is a static voltage that does not damage the device. And then you have transient specifications, and we say in what ranges you can use the device with a repeated excess voltage during the lifetime of the device. That's the first thing that we do. Then we have this, as I said, additional testing that we do to understand how robust is a device beyond the limit. So we have the qualification voltage, which is per JEDEC 80% of the device rating. And then we have the test to fail voltage that is variable. And that's what we needed to understand. And so this chart is really coming from data from our reliability lab. So you have time to failure and then the cumulative percentage of failure at different voltages that we needed to use to destroy the device. So that's a destructive test. So 1200 volt and more to get a device 700 volt destroyed at different times. Then we plot the statistics upon modeling on how this can be translated into lifetime. And what we can say is that, for example, if you take this technology and we use different operating points, so for a 700 volt device, 520 volt, 560, and then 700, we have all these years of lifetime predicted at different part per million or part per billion. So for 10 part per billion, we can exceed well above 10 years lifetime at nominal condition. So it's a quite interesting result. And this is for the drain, but we have similar data also for the gate stress and overvoltage gate stress. So the other important aspect, fundamental aspect, is the cost. So how did InnoScience reduce the cost of GaN? So the first point is to use a technology which is available in the market for years, which is silicon technology, which makes a substrate of our devices, and especially in 8-inch silicon wafers. Then we grow our epi. We are an IDM, so we do all in-house. We have factories to do this. And we are exploiting this economy of scale of substrate. I'm sorry, because there's some delay in the signal. The fact that we use an 8-inch wafer instead of 6-inch wafer gives almost a factor 2 available dies. And this means about 30–40% cost reduction with respect to other manufacturers in 6-inch. So that's the first thing. The other way to reduce the cost of the products is getting to high yield, of course, to exploit as much as possible the surface. So these are two parameters that we plot here. So there is the RDS on, and we see how constant is and uniform is the value across the radius, so across the wafer, and also wafer to wafer, so reproducible. And also for the leakage current, so a figure of merit of the quality of the technology is also very constant, and also wafer to wafer. So combined together, bigger wafers, proven technology, so also all the infrastructure, testing, laboratory, all the rest, plus high yield makes the cost down. The other important matter is standardization. So how can we let users at ease by using this modern technology? Is, for example, by using useful and common packages. So one is the DFN 8x8, and a DFN 5x6. And by the way, with the Kelvin contact, so to optimize the performance in let's say, high noisy environment. Then other packages like the TOL package, like the TO252. I know that's a bit peculiar. And then the TO220 and TO220F. Yes, okay. And yeah, so why do we have these packages? Because again, to make it easy for people that and engineers that have been using technology, and also in system that really wants to have the lowest possible cost, all these packages have an enormous volume production all over the world. So they are the lowest cost possible. So now a question would be, yes, but how is it not a bit contradictory? So we have a high-speed device, a high-performance device, and then use a package which is, let's say, higher inductance. Yes, it is true, but there is a trade-off depending on the use. where you can still be very effective, also with those packages. One example is a flyback of 65 watt, 100 kilohertz range, in which when you use DFN, like DFN 5x6, and you compare with the TO220, you can achieve basically very, very similar efficiency. It's a bit lower for TO220, but not dramatically lower. And here there are some examples when you start the design and you try to fine-tune and understand how to make it work properly with GAN, you will have at the beginning higher oscillations. But then by fine-tuning the driving circuit, you can get to a much better result. Sorry if I can show it. Okay. Doesn't matter. And basically you just fine-tune your gate resistance and then you get to a much better result. Now, for the low voltage and medium voltage device, we have packages that are in chip scale. So here the main interest is size, more size. And also flip chip QFN. So for, let's say, higher, it's even easier use for industrial systems, for instance. And bottom side cooled, but also top side cooled, also pretty new now. And yes, and LGA as well, both for discrete, but also for system in package. So the other point is the price, linked to the cost, of course. So when we compare, that's an exercise you can also do yourself. That's the beauty of that. So we take devices that you can buy off-shelf from distributors, like Richardson or DigiKey. And when you plot the price that you get versus RDS-on, you will see that InnoGaN tends to be even cheaper than the best silicon superjunction FETs that you can find off-shelf. So the message here is not that you have to take the absolute price here, because this price is, of course, higher than what you get when you go into a real project and you get a quoting. The message is that this is a trend that will accompany the technologies, the GaN technologies, to be as the same price as silicon in the market for the same voltage level, but with higher performances. And of course, price in a project will be much lower than this. One point about how to drive GaN. There are several technologies. One is the E mode, and the other one is D mode, usually with the cascode. I do not comment about what is better, what is worse, and that's not the point. I just want to say that we know the challenges of E mode, and we believe in the use of E mode. It has advantages from, let's say, controllability as well. And we give guidance on how to make design as robust as possible using E mode, either with discrete or with integrated devices. The first thing that we can help our customers and users with is how to drive with an existing driver. So you can have any, sorry. Yes, so very quickly here, just to say that we give guidance on how to interface an E-mode GaN in a safe way using an existing gate driver. I go forth. And the other way is to use system in packages that we have also introduced that allows customer to reduce dramatically the surface, the PCB spacing with the same solution. That's a half bridge and plus the 2 GaN FET that we are of 100 volt that we have here as an example. This means that you can take an existing application like here, a motor driver application, and make it much smaller by reducing to by 90% the total size and higher performances. Very quickly here, so how to introduce GAN in a concrete and existing project like a PFC. Here you see a discrete solution. You have a GAN FET and you can interface with the circuit that I just shown that needs to be optimized, or you can go directly with the integrated solution with a SCAPE, which has everything inside. Flexibility and faster. That's one of the latest that we have introduced, the ISG61OX, which is a 700 volt device. I will not go into details now. Just to say that one of the important aspects of this device is that it has integrated lossless current sensing that can be exploited in this way. Think of an existing flyback, for example. So this AirSense is mandatory for controllability, but also for safety, short circuit and so on. When you have a lossless current sensing, this is the advantage that you get. So you have in the system, you have in series two elements, the RDS-on of the GAN FET and the AirSense. Okay? And in some cases, the losses that you have on the sense resistor is as much as the loss on the GAN. So meaning that you can either increase the RDS-on over GAN, so saving much more money, or having much higher performances, just by this adding here.
Can I please go to conclusions?
Yes. So for, very quickly, you can extend also voltage operability with a multi-level approach. We have reference designs for that as well. So like here, we have an 800 volt converter with a 700 volt device. And very quickly here, demos that you will also see if you come to PCIM, like PSU of more than 4 kilowatt, all with GAN at primary side and the secondary side. I'm done. And for late driving as well. And I'm done here. So other examples, how to make like a thin power supplies for monitors and TVs. 300 watt, 1 kilowatt solution with for data center and industrial application, and also, of course, chargers. And I'm done.
Unfortunately, we have no time for questions. Yes. It's behind you.
I have. After all, I'm coming like a drunken man to this question. What about prospects of 1200 volt GAN? I was hoping to get that answer from you. Your previous speaker said impossible. What do you say?
Let's say that it depends. Possible or not possible, we will not comment on that. I can say that we are working on this, and we have already let's say, advanced platforms that have, let's say, then we see the implementation of that in reality. So, of course, we're not talking about qualified devices, simply because the main factor that we are following is to make the device usable, industrializable, and cost-effective. The thing is that in order to make it, to implement it, the size of the device at this moment is a bit large, and meaning that the price will be not that attractive. The first step that we're going through will be 800 volt and 900 volt. But from a, let's say, engineering perspective, we have proofs for 1.2K, 1.2K.
Thank you very much. Very optimistic.
Thank you.
Thank you. One information for you all. We have some margins because there is a mistake in the program. The dinner is at 8, and we calculate that we will finish here at 7. Between 7 and 8, we gather in the garden and have some drink. So we have some margins, 10 minutes or something. We can go over time for those who are staying for dinner. and even those who are going home if they want to stay longer. Okay.
I'm leaving now. So it's this is the size already tested. It's a DC-DC converter, 400 volt to 48 volt, 2 kilowatt.
So thank you very much. Now will be the last presentation in this device session. We're coming back to silicon carbide, and it will be given by Shubhangi Khadore from KTH. So, please.
Okay, so I think I'm audible. Hello, everyone. My name is Shubhangi. As he introduced, I'm a PhD student at KTH. Let me know if I speak too fast. And if the organizer can give me a heads up like 3-4 minutes before the time is over so that I can keep the speed as it should be. So coming back to the silicon carbide topic again, I'll be talking about the overcurrent capability of silicon carbide MOSFET, or SiC MOSFETs I'll be calling it. So I'm going to present few techniques and methods how we can enable the overcurrent capability for SiC MOSFETs. So this table is just to briefly introduce what kind of overcurrent capability we need and in what time range. So we can see that the overcurrent can vary from 10% to 64%. It really depends on the power system or the system we will be referring to. And these systems are discussed in detail in this literature if you want to see it more. And important thing to notice is that the higher the overcurrent capability we need, the shorter will be the duration that you can withstand before the MOSFET fails. So this was the takeaway of this slide. This is a standard structure for any of the power modules. I'll be discussing only this structure, which has bond wires, die, metallization of copper, ceramic, and base plate with the heatsink. And this is a chart showing where we need to do the modification for different time range for enabling overcurrent capability. So how we should read this is as follows. So if you want to increase the overcurrent capability in the range of nanosecond, millisecond, or the whole duration, you should focus on these areas. Either you can increase the size of the chip, you can even choose a new layout or metallization. And if you want to go a bit further on time scale, let's say from millisecond to second, then these are the techniques as in introducing metal, diamond, graphene. So that's how you should read this graph. So it depends on on which time scale you want to increase the overcurrent capability. And then that's how you can choose what to modify and how to increase it. So going on further, did I move too much now? So I investigated these materials. It's a big list, but not every material is that equally interesting. So from here to, sorry, my hands are shaking, but from here to here, these are all phase change materials whose melting point is much above 200 is above 200 degrees centigrade. So the reason I chose these materials was silicon carbide devices, they don't really fail until at least 250. They don't even fail even above more than 250 degrees centigrade. It is the packaging which limits it. So I have kept the upper limit as 250 degrees centigrade in all of my discussion. And below phase change material, these are highly conductive metals from copper, silver, gold, aluminum, nickel, and diamond, because diamond has exceptionally high thermal conductivity. So this is the same slide. Some of you might have seen it already yesterday in Professor Hans-Peter's discussion. So I did a general investigation about different materials. So let's say this is the semiconductor die. On the top of that, you can connect the heat absorbing material. It could be any of these material or a combination. And the thermal equivalent is as follows. I will be focusing more on the thermal aspects rather than electrical aspects for SiC MOSFET, because during overcurrent, energy or the heat generated is the limiting factor, because the temperature can go really high in few milliseconds, as I will discuss in further slides. So the power range I considered is 400 watts per centimeter square. It is just a future expectation of the chip that it's 1 centimeter by 1 centimeter, so 1 centimeter square of chip. I did analytical and COMSOL simulations to verify these the results I'll be presenting. So just for the matter, the copper, I investigated 200 milliseconds. So just to mention, I'll be focusing on milliseconds and second range of overcurrent capability. So for the copper, for 200 milliseconds, this is how the graph looks like. So let's say the overcurrent is applied at 0 seconds with an initial temperature of 100 degrees centigrade. And as the time passes, you can see that the temperature keeps on increasing. And the other material is, oops, I'm sorry. I moved a bit too much, I guess. So the other material is this phase change material. It is here in the list. Who's LI? Where is it? Yeah, it's the top one. So it is this phase change material, and you can see the thermal conductivity is extremely low as compared to the metals and diamond. This is the reason that the temperature, so the red curve shows the temperature on the top of the chip, or very close to the chip. So you can see within almost no time, the temperature of the chip will reach around this if we use just the phase change material. So definitely these materials are not the one which we want to use, although they have quite ideal characteristics, let's say the melting point, specific heat, but the thermal conductivity is the limitation here. It's much, much less than the metal. So this is the reason that the copper wins here among all these phase change materials. I'll be discussing more, but I seem to lose the control of this pointer. So this is the table summarizing the metals and diamond. I didn't consider phase change in this table for obvious reasons because they can't really help in this time range. So as we can see, almost all the thermally conducting materials, they have, this is the amount of material needed for 200 milliseconds to keep the temperature within 250 if the initial temperature is 100 degrees centigrade. It is just for the comparison to compare which material we're gonna use if we have to. So this is the same chart. This is the same information, but in graphical form, just to compare how much quantity of the material is needed for the exact same performance. And this is the one for second range. So if we keep on increasing the height of the material on the top of the chip, it will keep on, so the OC duration or the overcurrent duration will keep on increasing. But at some point of time, there would be a limit that there would be no further increment in overcurrent duration. So I have plotted this limitation here. This is the maximum OC duration you can have. And the amount of mass needed is this one. So that's how you should read this graph. So for instance, for copper, it's around 1.5 seconds and at a height of about mass of about 17 grams. This is the maximum overcurrent capability you can achieve in this time. So, and in this graph, it is also interesting to see that the copper being cheap is going to be our savior for increasing current capability, and diamond, but everyone knows how expensive a diamond is. So now I'll be briefly discussing all these investigations I did during last few years in my PhD studies. So the green ones are the technologies which we are going to discuss and the places where I investigated. So the first one is microchannel cooling, application of phase change material, heat absorbing materials, gate voltage augmentation. Phase change materials are the materials which change the physical state in order to have the application while melting. And heat absorbing material is a general term for any metal, graphite, diamond I'll be presenting. And the last one is gate voltage augmentation. So this is the power modules. This is the structure of the power module, which I will be having in all the further discussion. The dimensions are as follows. I took the footprint from one of the modules from Semicron, and I took the current and RDS-on rating from this module in order to calculate the losses during overcurrent. So just a basic information, the base plate is made of copper in this design. The upper limit of the temperature is 250 degrees centigrade. And this is the loss table I calculated. It's just a loss calculation for silicon carbide MOSFET. So this is the nominal current with 60% of margin I took the calculation for. So this is the amount of heat during nominal operation. And then for 2OC, 2OC means 2 times of overcurrent, 3OC, 4OC, and the losses are as follows. So the losses are going to be the same for every case I'll be discussing further. So the comparison of phase change material, I investigated 3 power module design. One is the standard modules without any modification. The other one is implementing a copper block below the die. It's important to notice that the copper block is much, much bigger in the design than the chip. Similarly, in the third design, I implemented a copper block with phase change material. The reason why I chose this design, the third one, is that because the phase change materials have very high latent heat and specific heat capacity. So I wanted to investigate, can I still use it by taking the advantage of thermal conductivity of copper and high specific and latent heat values of phase change material. So that was the reason I did this comparison. And this is just a dimension thing, size of dimension, dimension of copper block, phase change materials. And PCM used for silicon carbide is lithium. The reason is that the melting point is around 180 degrees centigrade and its thermal conductivity is around 200 watts per meter Kelvin, which is not as good as copper, but still almost half of the copper. It's much better than the PCMs or phase change materials I just presented. So this is the result of all the investigation. The first row is the standard power module, this one without any modification. And this is the duration it took to reach 250 degrees centigrade for 2OC, which is 0.75 seconds or 750 milliseconds. Similarly, for 3OC, the standard module has 30 milliseconds, and for 4OC, 10 milliseconds. As expected, as the OC increases, the duration decreases. So these are the numbers or OC duration for copper block, and this is the one for phase change material. The copper plus phase change material. Now it's quite interesting to see that the OC duration is almost the same for 2OC, a bit more the copper plus phase change. However, for the other cases, just copper block wins here. So the reason is again the thermal conductivity. So copper has much higher thermal conductivity than lithium. That is the reason it could actually let the heat flow through it very quickly. And since this duration is very low here for 3OC and 4OC, that's why the PCM or phase change material didn't have time to melt. That's the reason that the copper wins in this case. However, it's almost the same for copper block. However, one can argue that, okay, it's 100 milliseconds more, but look at the complicated structure, the difference in the complication. It is just a copper block. Here, you will have to do the manufacturing of this structure if overcurrent capability is aimed at this time range. So this was one comparison just to show the graph. So this red one is the standard module. The black one is copper block. So this gray one is the copper block and the black one is copper plus phase change. It's almost the same performance for 2OC. It is slightly better for copper for 3OC. Again, the similar performance for 4OC because these two are very quick transients. And let's have a look how much phase change material actually melted. So this red curve is 2OC, and you can see that in like 5 seconds, it melted on only about 70%. Because it had, let's say, 5 seconds to melt. But for the other cases, for 3OC, you will see a very small point. It was around maybe 1 or 2%, which got melted for 3OC. And for 4OC, it's a complete flat line. It didn't melt at all. So for this particular application, for this heat range, the copper wins as compared to phase change material. So this is one way of increasing the overcurrent capability. In my opinion, you can just use copper. Why to go for phase change material if you can achieve the same thing with the copper? Now, the second method is using microchannel cooling. So it's not a passive way how I present it. It needs something, but there will be some advantages and disadvantages of every method. So for the microchannel, here is the first structure that I am implementing microchannel cooling at the bottom of the chip. So I'll be referring it to it as a microchannel all bottom or MC on bottom. On the top, So I wanted to make the comparison, how good or bad is it to have it on the bottom or on the top. So this is the thermal equivalent of both the application. When it's on the bottom, the heat is coming from the top. When it's at the top, the heat is coming from the bottom. And the total thermal resistance can be calculated by using these expressions. So the number of microchannels I investigated are 5, 10, and 15. I wanted to keep it very simple from manufacturing point of view so that they actually can be implemented if someone wants. Yeah, and these microchannel blocks I assumed are made of copper, and I'm using coolant. Coolant is the material which will be flowing in these grooves and cooling the chip down. And this coolant is flowing only during the overcurrent. So these are the assumptions. And I'm using deionized water as coolant. And the flow rate I considered are 0.3, 1, and 1.73 ml per second. And these flow rates have been investigated previously in Switzerland with one of the research groups. So these flow rates are very easily achievable by a very small micropump using few milliwatts of power. So the comparison now about microchannel on bottom, microchannel on top, and there is a big table. Don't be scared, let's discuss this. So this is again the standard power module, which has this OC durations. And let's focus on the 5 microchannel first. So for 5, number of microchannels are 5, and there are different flow rates. So as you can see, the higher the flow rate, the higher the OC duration. So, and the second trend to notice is that for one flow rate and with different number of microchannels. So you can see 0.3 ml per second here is 300 milliseconds, and 0.3 ml per second is 700 milliseconds. And this OC duration increases with the increasing number of microchannel. And the whole table follows this trend, which I just showed. Another interesting comparison is the top and bottom now. So for the bottom, it's around 300 millisecond. It's much worse than how it was for a standard module, because you can see it is actually obstructing the flow of heat to the heat sink. While on the other hand, for top cooling, it's increasing quite a lot from 0.75 seconds to 3 seconds. So if you really have to compare the top and bottom, for every configuration independent of number of microchannels, independent of the fluid rate, the top cooling is much better. The further details are given in these two publications as well, or I'll be here later as well. So, and then there is like third investigation. There is this third investigation where I investigated these 4 power module designs. One is the standard, again, the same module which I was talking about. The other one is when the material is being used at the bottom of the chip. The other one is the top of the chip. And this is one of the most interesting things which I noticed in this investigation is when I applied heat absorbing material on the top as well as on the bottom. So these are the electrical equivalent of the thermal circuit. So for standard module, this is the power being dissipated and the thermal resistance is there as with respect to ambient. For the bottom, this resistance of this block will come in series to the ambient. And for the top, there are 2 parallel paths for heat dissipation. And for this configuration, it looks like this. There would be a parallel path as well as some thermal resistance in the series. And this is the heat flow for the module structure C and D, that there would be some heat flow on the top. So the materials I investigated in this study are copper, graphite, and aluminum. The reason copper is cheap with very high thermal conductivity. Graphite has extremely high thermal conductivity as compared to metals. It's around 4 times more. And aluminum is another cheap material, so I just wanted to compare. I used the standard solder material because it was the one which I got the modeling for. And the heights I'm going to consider is 1.62 mm, 5, 10, 15, and 20, because if you go further than that, there is going to be increment in the parasitic inductance. Although you may get overcurrent duration a bit higher, but the other factors will come into the picture. So let's see how it looks like for the copper at the bottom. So the darkest red is the one with standard power module. All the green curves in all the curves represents that there is an improvement in the OC capability. And all the red or the red variations in all the graphs show that there is no increment basically. It's making even worse than the standard power module. So for the copper at the bottom with the same dimension as that of the chip, there is basically no increment. It's actually making it even worse. For the top, it's increasing. From the legend, it can be observed that the higher the height, the higher the OC. But at some point of time, the increment in OC duration will not be as much as the increment in height. So we can actually cut it off at a particular height when we see there is no more increment. And the last one, and one other important aspect is the temperature. So in all the graphs, the overcurrent is applied at 60 seconds here in all the graphs. So before 60 seconds, the standard module here for the top arrangement has the least temperature, and this steady state temperature keeps on increasing as the height increases. However, for the top, this steady state temperature is less than a standard module, which definitely enhances our reliability and performance in the long term and also increases the overcurrent capability. And for the structure, which has the heat absorbing material on the top and bottom, the performance and the duration, steady state temperature, they are in between these two structures. The similar observations are made for 3OC. I think we can see all the green curves are increasing the overcurrent capability. And similar graphs for graphite, just for the information, I plotted a lot because you will see why in this table. So this is the table which tabulates all the overcurrent durations for different heights and for different arrangement for 2OC, 3OC with a different height. The left one is the copper, the right one is the graphite. So we can observe here for 2OC, let's say, the OC duration keeps on increasing, but the increment, the delta OC duration is getting smaller for every 10 or 5 mm of height. Similar observations are made for all the rows. One important and interesting aspect in this is, since as I mentioned, graphite has the thermal conductivity, which is 4 to 5 times more than copper. So at least I was expecting that the OC duration will be much larger for graphite. But just have a look here. For 20 mm, for top case, it is 6 seconds. And for 20 mm for graphite, it is just 3.3 seconds. Anyone would like to guess why is it so, even though the thermal conductivity of graphite is much, much higher? Any guesses? No? Okay, it's the density and the specific heat capacity. So the density of the graphite is around 4 times or 5 times less than copper. So the total thermal mass available with the copper was much, much more higher than the graphite. So basically, you have the way to take the heat out, but you don't have the capacity to put the heat in. This is the reason that the copper again wins here. So the reason is this. And this is just for the comparison, how much is the overcurrent duration for different materials. I think we are running out of the time. Yeah, so I will quickly wrap it up. You can ask me later if you have more questions. So this is the amount of overcurrent duration for different heights for 3 materials, copper, aluminium, and graphite. This is for 3OC. The similar trends are observed, but at a different scale. And the takeaways are as follows. The top cooling is the best in terms of steady state temperature and the OC durations. Bottom cooling is the worst, at least for the same dimensions as that of the die. If you really have to use bottom cooling for some reasons because you want to put bond wires or something, then you have to have much more heat absorbing material below it, as we saw in the phase change material comparison. And the maximum height of 20 mm is, let's say, the limit due to the increased parasitic inductance. And I would very quickly introduce one last method, gate voltage augmentation. As we know that RDS on decreases with the increase in gate voltage. So when there is an overcurrent, we can increase the gate voltage momentarily, or let's say for a very small duration of time, so that the RDS on decreases, and hence the conduction losses can be either kept constant or can be decreased. And switching losses during overcurrent can be reduced by reducing the switching frequency. We tested some devices in the lab for its rated. These are the devices from onsemi, which were rated for 30 amps. And as I just mentioned, this is the RDS on decrement for the increment of VGS, and we could test up to 50 volts because the device failed after that. So this is and I used the simulation in the LT-SPICE for 2 different kinds of model available from the manufacturer to show how the RDS on decreases with the increase in gate voltage. The takeaway here is that we can use the models available from different manufacturers to predict how much RDS on will decrease. So we can actually estimate how much overcurrent you can handle. And this is the table which shows the reduction in the conduction losses. I just tested pulse, so there is no switching loss in this investigation. Oops. What happened? Last one slide. I know we all need a break now, but trust me, it's not going to be more than 1 minute. Okay, so this is the last slide, which tells about the application of gate voltage augmentation for overcurrents. So this dashed one is our standard gate driver, where we implement plus and positive and negative voltage. But we can implement additional feature, just like the way a desaturation function is implemented, that the gate voltage increases only during the overcurrent. If we can implement this method, we may be able to handle the overcurrent using just the gate voltage without even modifying the module. I haven't done the simulations of this, but it is just the beginning of this thought, basically. So this brings to the end of my presentation. If you have some questions, I would be glad to discuss.
Thank you. I think we are really out of time now.
But I'm going to be around, so you can touch
maybe you can catch like you in the corridor and ask all the questions and discuss.
Yeah.
Thank you very much.
Thank you.
Okay, ladies and gentlemen, the coffee break is over. We can look forward to a very interesting session on modeling. And our first speaker now is Dimosthenis Pevtitsis, and he's going to talk about real-time silicon carbide MOSFET device models. Please, the floor is yours.
Thank you very much. Thank you very much, Hansi, for the introduction, and thank you for inviting me to deliver this presentation at the SCAPE this year. So, at NTNU in Trondheim, in Norway, we focus a lot on designing active gate drivers for silicon carbide MOSFETs, especially focusing on power modules. And we there look both at active gate drivers using the current source, a current source or a voltage source, active gate drivers. And you see here some examples. For example, this one is a current source based adaptive gate driver, and that one is a voltage source gate driver. But I'm not going to talk about gate drivers today. The main motivation today is to show you how we approach the modeling and simulation of silicon carbide MOSFETs. And all started a few years ago when we tried to evaluate the switching performance of silicon carbide MOSFETs using our adaptive gate drivers. And there we soon realized that using the conventional SPICE-based simulation platforms results in very long simulation times. So here you see an example of simulating a double pulse test circuit for 600 microseconds usually requires tenths of seconds of simulation time. And on top of that, one should also consider the problems with the convergence, with numerical convergence. When you don't reach a convergence, the simulation basically stops. And also, doing this kind of simulations, one needs powerful computers. And as you see here, we faced no convergence for specific switching transients or DVDT values, rate of change of voltage. Of course, in commercially available real-time platforms that I guess most of us are familiar with, we can use this kind of platforms to really accelerate the simulation process of systems. But the main disadvantage of those is that you need a dedicated real-time simulation platform, which usually comes at a high cost, and also you are limited in system-level simulations. So you don't really go into the switching transients that we would like to monitor using such a simulation model. So we tried to develop a different approach, and what we did, we got the SPICE simulation approach, the same expressions that typical SPICE platform use, and we transferred this model to the so-called field programmable gate array processor, or for short, an FPGA. And why we did that? Because FPGA is a key component for converters. It operates as a controller, and it can also be a key component for controlling the switching states in an active gate driver. So we did basically transfer the model from there and implement it in the FPGA. And in this way, we can run the converter in or the silicon carbide MOSFET model in real time, so we can accelerate the simulation, and we can also achieve numerical convergence, as I will show you later in my presentation. And there are two options emerge. The first one is to use this model for rapid prototyping or mainly evaluation of silicon carbide MOSFET and gate driver, a combination of gate driver and silicon carbide MOSFET. And this is done using the FPGA platform, that is this one, and monitor the different states, the switching states of a MOSFET using an oscilloscope. And the second opportunity is to use or to integrate this real-time model with the FPGA that sits on an active gate driver. And in this way, we can use it as a basis or as a foundation for developing a digital twin that can be used to monitor the load current and the blocking voltage, and give, for example, the rate of change of voltage or the losses, and all monitoring parameters that one would like to monitor. So how we approach this modeling? First, we start from the channel current expression. So we didn't really develop our own expressions here. We just utilized the mathematical expressions that a typical SPICE model uses. So it's the Seaman and Hodge model expression for the channel current and the dynamic model expressions. And on top of that, we also characterize the device under modeling or under study statically, which means that we use a power device analyzer and capture the parasitic capacitance and also the static transfer characteristic. And the last step was to discretize the different differential equations. For example, here you see a lot of differential equations, and discretizing them allows us to come to a FPGA, and using, that's an example case here. So we use a suite that goes together with the Xilinx FPGA that we used to demonstrate this modeling approach. And we use the Simulink toolbox to actually generate the intellectual property cores, the IP cores as they called. So that's modules of code that one can download in an FPGA and let them run there. And then these IP cores that are basically a bit stream of zeros and ones, we download this to the FPGA, and then the model can run in real time in an FPGA. You can either monitor here with an oscilloscope or integrate it in a gate driver. So that's the approach. And using the same FPGA, I mean, there is this platform that the FPGA sits on, and that one has an input-output interface, so digital to analog converters that one can just plug the probe and monitor the model states. For example, the drain source voltage or the drain current, the gate source voltage, or even the switching energies. So the entire module is now modeled in a FPGA. And to validate the model, we went for two different approaches. The first one that you see on the left-hand side of the slide, we compared the double pulse experimental results from a given power module with a real-time model. So we tried to, we characterized statically the module, and also integrate the expressions in the FPGA as I showed you earlier, and then compare the switching transients experimentally and from the real-time model. And the second approach was to use the same real-time model and develop a dual active bridge, which is one of the standard isolated DC-DC converters that process high power, and try to compare how the real-time model can really make a difference when comparing an ideal model of a dual active bridge with the model of a dual active bridge that is built with a real-time model, and where the non-idealities are considered. So here are some results from the double pulse test. Here you see the turn-off switching transients at 1 kilovolt and 640 amps of current. And we see that the blue one, that is the model, and the red one is the experimental measurements, match quite well. There are still some mismatches here and there, but overall, when we evaluate the turn-off energy, we achieve more or less the same value. It was 1.4% off. And the same for the turn-off falling time, which is an important parameter when designing a converter and deciding about the switching frequency and the dead time, for example. Turn on at the same testing conditions, more or less, 1 kilovolt still, but 500 amps. Still got a quite good matching of between the experimental and the real-time simulation model results. And the same for, it went quite fast. So at 800 volts, so a little bit lower voltage, and more or less the same current. We have some mismatch there, which might be due to the fitting error in the expressions from the static characterization. So this is just a matter of improving the fitting of the model of some expressions. And here you see the last one at 800 volts, that is a turn-on transient. So gate source voltage, drain source voltage and current, and the switching energy or losses. And then we also evaluate the real-time model to assess how the non-idealities of SiC MOSFETs impact, for example, the overall design of a DC-DC converter and the and tuning of the control system. And here we see that, so we simulate this converter in using ideal switches and the same, and compare it with a real-time model. And there we see that for example, the charge that is stored and released from the devices impact the output voltage. And as you see, there is a little bit of mismatch between the ideal voltage and the current. So the voltage here and the inductor current in the dual active bridge there. So there is always a small mismatch, which is expected, but using a real-time commercial platform that uses or considers ideal components, you cannot really capture these differences. And then to show the universal characteristics of this model, we also use the same model and different static characterization from a 1200 volt half-bridge module. I think we are all familiar with that. And here we again try to compare the switching transients, both turn on and turn off. What you see here is the turn on process. And one thing that is demonstrated clearly here, and it's basically one of the limitations of this modeling approach, is that if you here observe the red waveform, that's the drain source voltage, and that one as well, and the current, you see the steps or the calculation steps, and this is basically one of the limitations with this approach. You have to accept that the maximum calculation step in an FPGA is determined by the clock frequency. So if, for example, you have 100 megahertz of clock frequency, then the minimum time step is equal to 10 nanoseconds. So 10 nanoseconds is the resolution of what you observe here. So here, it's clearly shown that, okay, the chosen FPGA platform is not sufficient to capture the high resolution drain source voltage and drain current of this module. And the main reason here is that this one has a much lower inductance, commutation inductance, and this also means that with a given driver design, we can reach much shorter transient times. And this is mainly the problem in this one. But with the advent of more powerful processors, there are a lot of such available these days for machine learning applications. I think one can really go much faster there and get a nice resolution if this is needed from the application point of view. And this brings me to the summary of my talk. So what I presented is a real-time model for the switching transients of a power module, of a silicon carbide power module. In that case, I forgot to mention that we used a 3.3 kilovolt 750 amp module. And with this model, we accelerate the simulation time. So 1 second of evaluation time for the circuit requires 1 second of simulation time, which is a much faster simulation process compared to the traditional platforms. And at the same time, we eliminate numerical convergence issues. And the main reason there is that we use an explicit solver method, which means that, or the FPGA use an explicit solver method, which means that the current state is always calculated using the previous state, which is not exactly what happens in a SPICE-based simulation, where there is an iteration of the solver to reach a solution. And on top of that, we have the possibility to integrate these real-time models with active gate drivers, and evaluate them, or evaluate active gate drivers, which was our initial goal. And and finally, it's also possible to use it for monitoring converters' performance during the design phase and evaluation phase, because of the opportunity that we can assess the non-idealities and their impact on tuning the converter and designing the converter. So with that, I would like to acknowledge my PhD students who contributed to this work. And thank you very much, and I'm very glad to answer questions.
And I'm very glad to say that we actually have time for questions. Do we have any? Okay.
Have you considered the parasitics? Because in your real time, even for validation, you have some parasitics that is not relevant to the, for example, power module or device that you have. Mm-hmm. Have you implemented that on those parasitics also in a PGA, or you have excluded that from that?
No, we did
maybe you say the question so the other ones hear the question.
Yeah, so the question is whether we consider and integrate and added the parasitic components in our modeling approach. And I will go, or maybe I don't need to go, but I can go back. Yes, we did consider the parasitics, not only the static. Okay, this doesn't work, so okay, it's here. So we characterize the given power module in advance statically using a power device analyzer, which is one approach to do so, to assess the input-output reverse capacitance over the drain source voltage and so on, and the static transfer characteristics. And on top of that, we also include the commutation loop inductance in the model. And all these parameters sit in the FPGA. But now another important aspect emerged here, because What we are trying to do at the moment is to co-simulate, so to have a powerful computer sitting there and an FPGA sitting there and communicate those two with a JTAG, and that is shown somewhere later, and try to run the heavy model on the FPGA and the light part of the model, for example, some parasitic inductances in the circuit loop on the computer. So that's an ongoing work together with some colleagues in Aalborg University. So, okay, it goes up and down, sorry for that. It's quite, okay, it's here. So you have a possibility to connect to the computer. But you can expand the model as much as you like if you want to include more features or more characteristics in the model. That's possible, given that you have a sufficient powerful FPGA.
Yes. Are you ready for another question?
Oh, yeah, sure.
Good. Thanks for a really interesting work. Do you think this could be the way or the tools to use for health assessment and aging of components and systems, because that is expected to be a very important subject in future?
Yes, that is something we thought afterwards, because first we thought how to monitor the overvoltage, for example, and try to do something on the gate driver side and minimize overvoltage. But then later on it came this question to us, so how we can integrate a reliability model with this. That's possible. I think Professor Ludwig will talk later about reliability, but it's very possible to integrate a reliability or a lifetime model in the model here and monitor the, for example, the state of health of the packaging reliability, which is important, or even how some parameter shifting happens in the MOSFETs. The only thing there is to consider the time dynamics, right? So how fast the real-time model of the reliability should be compared to monitoring the individual DVDT and DIDT. But it's possible, yes, and we have thought about that. So you can expand the model as much as you like, provided again that you have sufficient power on the board. And there are such boards from AMD, for example. Recently I saw a couple.
Okay, thank you very much.
Thank you.
I think we stop there. So now it's time for the next speaker. And this is Konstantin Kostov from RISE. And he will be talking about modeling of power modules. The floor is yours.
Thank you. The co-authors of this presentation are visible there. So these are my colleagues Sid, Lakshmi, and Hitiksha, who helped in different phases of this work. So what I'm presenting is a project that we started 2 years ago with Volvo. I'm not sure was it Volvo or RISE who initiated it. At the first phase, we made a study or review of all power module technologies. What we call the state-of-the-art power module is shown here. The best example of such classical power module with all this base plate, bond wires, and what you see here. The best example in terms of layout, I'm talking electrical layout in terms of parasitics, is this module from Microchip here that you see. They claim something like 2.9 nanohenry parasitic inductance, and believe it or not, it's true. Actually, the best technology in terms of parasitic inductance is the semicron, which you see here. They use the flex foil. But this is advanced technology. I'm mentioning it here. So the alternatives to the state of the art in the single-sided cooled power modules, we see them mostly on the top die attach. You can see that the aluminum bond wires are replaced with copper bond wires. You see that in Danfoss bond buffer. And I think already many years ago in this conference, Japanese groups were reporting about copper bond wires, and they were reporting, was it 10 or 20 times higher reliability and lifetime? And I have heard Danfoss people claiming the same. They're absolutely confident that their technology is the most reliable one. Professor Lutz is the expert here. Maybe he can comment on that. The other alternatives, later we saw the copper clipped, and Vitesco uses silver clip. And then the other top die attach advanced technologies, we see the skin technology from Semiclone that I already mentioned. And then we move to the double-sided cooled power modules, the alternatives there. You see here the module from ST, which if you search on internet, you will not find, but we got some pictures from a report from YOL, System Plus. I don't know if they're here. So this is the module with the copper spacer or copper molybdenum alloy. And another module, double-sided cooled module that you can see. Also, if you search for Hitachi power modules, automotive modules, you will see something like with this layout, single-sided cooled, like what you see in Danfoss. You don't find this one, but Hitachi has a double-sided cooled power module. You see it here. You can find it also in some publications for double-sided cooled. And finally, in a different alternative, I have to mention the embedding. And I was surprised that Schweitzer is also here. We mentioned them in our report to Volvo 2 years ago in this phase. And then we are moving to the phase B, which ends this month, and which I will present now. So this is the design workflow and layout optimization, the way we do it. So I didn't show agenda because my agenda is here. In red, you will see the point that I'm presenting, and in gray is what's coming. So an example of power module, you start by creating the geometry. It can be done in any CAD tool. I do it in ANSYS because I use ANSYS for the simulations. But these simulations that I do in Q3D in ANSYS, it can be done also with other software. For example, Altair. I learned not long ago that they can do the same. So if it looked pretty simple, that box that you saw first, that was this double-sided cooled technology. When you strip it from the top substrate and the molding, you see here the layout. And then comes the simulations that to obtain the parasitics of the package, which, as I said, I do in ANSYS Q3D. So you can think of the power module as conductors separated with the electric. And we have the electric in the substrate, which is one thing, the two substrates in this case. And you have also the molding compound that fills the module. So these are the two dielectric that we have. And of course, when you have conductors separated by the electric, you have a capacitor, which can be modeled as a parallel connected conductance and capacitance. These two elements in the parasitics. The other two parasitic elements, the resistance and inductance, they're along each conductor. So you can model this simple, small thing, the power module. As a filter, it can be, you can think of it as a T filter with many, many sections. The higher accuracy you want, the more sections you have to add to that. And also with many lines, depending on how many terminals you have here. So, and I'm mentioning here a few things. So these parasitics, they're frequency dependent. Many of you who have been working on this or have heard presentations on this should know that the resistance and inductance, they're frequency dependent. Also the conductance, that is the conductance between the conductors in the parasitic, the conductance between the conductors in the module. Since this dielectric that separates the conductors, if you look the material properties, you will see with the frequency this conductance changes. For the resistance and inductance, the main reason for changing of these parameters with frequency is the skin effect. Since we don't have a whole day to go through all the details in this modeling, I will mention just I already mentioned there is capacitance, which is often neglected, but it plays a huge role. When you think about this T filter that I imagine, of course, the frequency behavior of this T filter doesn't depend only on the resistance and inductance along the conductors, it also depends on the capacitance between the conductors. And the ground planes that we have, the heat sink is usually grounded, so the ground planes that are also conductors. So this complex T filter that I was describing is here, but now we are focusing only on the inductance because there are a few points I want to stress here. When Q3D models the package, it takes into account all these parasitics, this complex system and when you think of the example that I just gave, it was half bridge with 8 chips per switch position. That is 16 chips altogether in the power module. So this kind of system, you have 50 by 50, this matrix of parasitics resistances, and the same applies also for the resistances, is 50 by 50 matrix parasitics. For the capacitances, it would be 5 by 5. And if we have Kelvin sources in the chips, and I can tell you that it seems the automotive manufacturers are forcing the device manufacturers to use this layout that you saw earlier. I saw it in onsemi, I saw it in Wolfspeed, I see it in ROM. They all, if you look their latest chips with 5 by 5 millimeters, they have the same layout. And I think the automotive manufacturers like Volvo are pushing them to go to this layout, to have Kelvin source. But if we have Kelvin source, this system of parasitics, this matrix of parasitics will become 64 by 64. So now, I don't know about you, but I cannot, from this complex matrix, determine the stray inductance that is given in the data sheets. And I can go through the equations and show you that it really, from the matrix alone, you cannot calculate it accurately. But to demonstrate it easily, what we do here, so this is the half bridge with, in our case, as I said, we have 8 chips per switch position, but they can be even more. We have modules from Hitachi for higher power with 16 chips per switch position, so altogether 32 inside. So when you consider, so this thing here is just the plus plane, from plus terminal to the drains of all these chips. So you can think of these parasitic inductances here along this conductor as parasitic inductances in parallel. You see them all on this main diagonal here. And of course, when they're in parallel with these values that you have, you get this value by counting as if they're in parallel. In the ideal case, if they're equal, these parasitic inductances, you divide by 8 and you get this value. So roughly, this inductance here from plus to drain in this equivalent circuit would be 1/8 of the values that you see here. And if you do the same thing also for the phase, which in this case will have 16, it will be 16 by 16 matrix. In the whole module, the matrix, as I said, is 50 by 50, and you have these submatrices inside, which represent different conductors. But anyway, because Mietek, who always, when he models a module like that, he creates an equivalent semiconductor that represents all these chips as one chip. And then he wants from me simple parasitic, so that he can add the strain inductance on the DC link, and then these strain inductances that you see here in this equivalent circuit here. And in the past, I was trying, since I can't give him reliable data based on this huge matrix, I'm taking the main diagonal and I give him these values. And I can tell you that this approach is wrong. So for at least 2-3 projects, I have been misleading Mietek, and it's not on purpose. I can explain it now. With this approach now, when we reach this simplified half-bridge circuit, we can go further to this simplification. Actually, Par Randstad likes exactly this thing here. Now, if we add the strain inductance that is given in the data sheet, if this calculation based on the main diagonal and the parasitics matrix is anyway accurate, the strain inductance would be the sum of this. Basically, these two come here, and then this source and drain inductances, they are added here, and then the strain inductance is simply the sum of L1 and L2. So in this example that I'm showing here, if we add this, we get 2.59. The alternative way to do this is by shorting the chips, and then you measure the inductance from plus to minus, and we get 10.1. This is for this example that you see here. So pretty big difference, as you can see. So I hope that demonstrates the problem. So let's move to the next. So when we have this model of the parasitics, which comes from ANSYS Q3D, in this case, then we can perform double pass test simulations. This can be done in ANSYS. They have their own circuit simulator called Circuit, and it can be done also in SPICE. Until now, it could only be done reliably in ANSYS Circuit, because if we export the parasitics from Q3D, if we export SPICE model in the old versions of SPICE, of ANSYS, of Q3D, you get a SPICE model for a given frequency. You can select which frequency you want, but it's a given frequency. As I said, the resistances, inductances, and conductances in the model, in this parasitics matrix, are frequency dependent. So that means we lose this non-linearity, and then this exported SPICE model, you can import it in LT SPICE and simulate. So in the latest version of Q3D, they have something called beta. So you can export a SPICE model that preserves this nonlinearity. Okay? I use circuit because of these historic reasons, as I mentioned. In circuit, we have to import the SPICE models of the chips. Where is the pointer? Yeah. These symbols here, they have SPICE models behind them. And Q3D, this block that you see here in the middle, that represents just the packages with their parasitics. And then we can perform the double pass test and get the switching behavior. Here you can see the switching behavior for two different gate resistances. As you can see, this is without any gate resistance, a lot of oscillations. When we add some gate resistance, this is actually equivalent to 8 ohm resistance per chip, if you look about that, because there are 8 in parallel. So you can see the oscillations are a lot less, but also the switching, the switching time increases significantly, and from this double pass test simulations, we can calculate the turn on and turn off energies, also the conduction drop. So to estimate the conduction, the voltage drop in order to get the conduction losses. And we need this information for these Plex simulations, where by simulating the double pass test for different voltages and different DC voltages and currents, we create tables like this. They look something like this. What you see here for turn on and turn off, similar tables. You can see for different temperatures. And these are the tables of turn on and turn off energy losses. This is the conduction losses. Another thing that Plex needs is the thermal chain. And then with the Plex simulations, we can get, the maps of the loss maps for different operating points. In this case, we had the inverter model connected to a motor, so the x-axis here is the RPM of that motor. And of course, since we have the losses, we can also calculate the efficiency map. This is the comparison of several layouts. The one that I show already. This is the double-sided code with spacers. This is a single-sided code. This is not exactly the microchips module, because it is the same layout, but we want to use the same parameters, things like trace width, clearance between the conductors inside the module, so that to make a fair comparison. So also the same chips. So it's not exactly replica of the microchip module that I showed in the beginning, but it's the same layout. And this is when we strip that from the packaging. And then another version of double-sided code, we call this flip chip design, because the chips here, they're all laid with their drains on the bottom substrate. And that requires extra space for these spacers to move the current from the bottom to the top and back to the bottom. This is not necessary, in my opinion. So we can have the chips from one switch on the bottom substrate and the chips on the other switch on the top substrate. And we end up with something like this if we want to have Kelvin sources. So this is what we call the flip chip double-sided code design. And the results are if we compare these different designs, you can see that the single-sided cooled design actually shows pretty good, because of the low parasitics. It shows, it is much better in terms of parasitics, but we cannot give definite answer which one is better, because the double-sided cooled designs are cooled better. So, so this is the final slide from me. If you have questions.
I don't think we have time for questions, actually. Sorry. Okay. Thank you. So, our third paper will be presented by Saeed Akbari from RISE, and the title is Lifetime Modeling of Power Modules.
Okay. Good afternoon, everybody. Okay, so this talk is on lifetime modeling of power modules, and it's part of the project that my colleague Konstantin described in the previous talk. So here I'm focusing on lifetime modeling of double-sided modules. These type of modules are increasingly used in electric vehicles due to their potential for lower thermal resistance and lower parasitics. And here is an example from Infineon. Basically, if we look at the structure, we have a second ceramic substrate at the top, which is connected by using some spacer to the device. So the difference is that in single-sided modules, we have a single layer of die attached between the die and the bottom ceramic substrate. But here, by introducing spacers, we are creating additional interconnection layers between the spacer and top ceramic substrate, as well as between the spacers and the die. And here is another example from ST. So the question is here, how is the reliability of double-sided modules compared with single-sided modules? There are some previous reports that have shown failure of these modules during power cyclings in these new interconnection layers between post or spacer and the bottom substrate or the die. And here's another example showing the failure of silver interconnection layer between the die and the spacer. So we created a finite element model to compare these different versions. If we compare in general thermal performance of single and double-sided modules, looking at this table, the reference design, if we consider it in single-sided modules with indirect cooling, which means we are using thermal interface materials like a thermal grease between the module and the heatsink. So if we consider it as the reference design, then by using double-sided modules indirect cooling, we can potentially lower thermal resistance by 30 and 40%. And even by using direct cooling, by directly soldering the heatsink to the module, we can even lower it. And the minimum can be achieved by using direct double-sided cooling. So on the both sides, we are not using thermal grease. We are just soldering or sintering the heatsink to the module. So we know that this module has the best thermal performance, but how about reliability? Are we confident that it works under power cycling? So for reliability simulations, first we need an appropriate material model for the die-attached layer. So here we considered silver sinter layers, and we describe them using an viscoplastic model, which describes inelastic deformation rate as a function of stress and temperature. So basically here, damage, we define damage as an inelastic strain accumulated in a power cycle. So in summary, damage is a function of temperature and stress applied to the silver sinter layers. So in a constant temperature, if we increase stress, we get more damage in the interconnection layers. And also in a constant stress, by increasing temperature, we get the same. And we know that temperature depends on the thermal conductivity of different layers. Obviously, depends on power loss and also on the layout, if the chips are too close and we have thermal couplings between the chips. Also, stress is very important. It depends on the CT mismatch. We always try to minimize CT mismatch between the neighboring layers to minimize damage in the bonding layer. And also, this stress depends on mechanical constraint. We expect that, for example, in double-sided modules, we apply more stress to the interconnection layers. Also, in direct cooling, we may introduce more stress and pressure to the bonding layers. So after we calculated this damage parameter, we can use it in a lifetime model to calculate the number of life cycles to failure, this type of Coffin-Manson equations. So we started with a simple model just to compare single and double-sided modules. We calculated damage distribution along the bonding layer. So x-axis is defined from the left edge of the die-attached layer between the silicon carbide chip and the ceramic substrate for both single and double-sided modules. And here we can see obviously that we will have more damage in the double-sided modules interconnection layer. And it's obviously, as I explained before, it's because we apply more pressure using this top ceramic substrate and a spacer to the die-attached layer. But to calculate this more accurately, to calculate lifetime, we need to model the entire power modules because all the chips are interacting with each other. So here is an example. I'm just showing all the die-attached interconnection layers. For each device, we have 3 layers of silver. Top silver layer between the spacer and top substrate, and the middle silver layer, the green color, between the spacer and the die, and the bottom silver layers between the power die and the bottom substrate. So we have 3 layers of interconnections per power die, and we have 8 dies per switch position. So in total, we have 48 layers of these silver layers, and damage can start anywhere. So the question is, can we use simulation to predict the location of damage and the number of life cycles to failure? So we did a coupled thermal structural simulations in ANSYS. First, we calculate temperature distribution in power cycles, and then we exported the temperature data to the structural simulations. So 3 power cycles was applied to get the temperature distribution in all different bonding layers. And then we can see layer by layer how is temperature distributed in these silver layers. And the next step that is important is the structural simulations. We have the temperature data. Here is a lot of focus on describing the different layers using accurate material models, but we have to pay special attention as well to the boundary conditions that we have for our power module. How is it connected to the heatsink? How is it connected to the power terminals? It could have a very large impact on damage distribution and lifetime. So the first structural boundary condition here is power terminal connections. Typically they are connected using screws or they are welded, but we do not want to model the screws to make our model very complicated. It already has a lot of details, and so to model these power terminals, we just need to fix the internal surface of the power terminal holes. And the next one is heatsink mounting pressure. If we look at the assembly instructions for heatsink mounting, we typically can find how they fix the heatsink to the power module, how much pressure is applied using this clamping structure, and then we can, in a model, apply the same pressure to the top and bottom surface of our power module. And then the other point is about heatsink bonding method, direct cooling versus indirect cooling, as I explained, how we are going to model the bonding layer between the heatsink and the power module. Because here we are not modeling any bonding layer, how we are going to simplify that. So if we consider the top surface of the top and bottom, top substrate and bottom substrate, in two extreme cases, we can define free support or fixed support. Free support means that the surface can easily deform and move in all directions. So basically, there is no constraint. And in the fixed support, it means that the surface is completely fixed and it has no degrees of freedom and cannot deform freely. But reality is never this or that. It's never free, never fixed. It's something in between that we, in solid mechanics, we define as elastic support. Basically, we assume that there are some continuous springs distributed at the top and bottom surfaces. We do not model them. We just virtually consider them. We assume that they have some stiffness, and the stiffness of these springs is defined by the Young's modulus and thickness of the bonding layer. For example, for a 100 micron thick thin with 1 gigapascal Young's modulus, we can this value for the stiffness. And then lifetime predictions with all this, we can get the damage distribution in all these interconnection layers, and then lifetime cycles to failure for each layer. And the important point is that sometimes we might just model a single die or spacer and use some kind of symmetric boundary conditions, but in reality, there is some structural coupling between the neighboring joints. It is similar to thermal coupling. When one chip is activated, it can affect the temperature in the next chip here. When we have another rows of chips, they can increase damage in one reference chip. And using this model, we can do some parametric study. For example, what is the effect of, what is the difference between direct cooling and indirect cooling? In the x-axis, we increase the stiffness modulus of the bonding layer from a very low value for silicon thermal interface material or epoxy and increase it to a much larger value related to solder and silver. And we can see that as a result of that, we get much larger maximum damage in the silver interconnection layers. And this can significantly lower lifetime of the interconnections layers. So direct cooling from both sides could have a very severe impact on lifetime. We expect at least an order of magnitude lower lifetime when we use solder for bonding heat sinks. And another example of parametric study that we can do using this model is heat sink mounting pressure. When we increase it from 100 kilopascal to 100 megapascal, there is a transition between 10 and 100 megapascal. We get a much larger damage and lower lifetime. But typically, the heatsink mounting pressure is not a concern. The pressure is typically less than 10 megapascal. And this was the last slide of my talk. Thank you very much.
So, we have plenty of time for questions. Okay.
Hi, thank you so much for the interesting presentation. I have one question. So basically, double-sided cooling reduces the junction temperature in normal operations.
Yeah.
So what I would imagine is increased reliability. But at the same time, as you just showed, that reliability decreases. So how is it really the overall impact that if I apply double-sided cooling? So there are two factors, opposing ones basically. One is increasing the lifetime, another one is decreasing the lifetime. So what is the result overall if it happens in the reality?
So yeah, there are two parameters affecting each other. The maximum, the thermal resistance. Here we assume that one parameter is fixed, the maximum junction temperature. Yeah. We assume that power module is working at its best performance, and then we calculated because this is what we expect, and then we calculated lifetime for that. If the power loss is the same, then we can expect different results.
So we can't say clearly if the lifetime would be increased or decreased by double-sided cooling. It really depends on how it looks like in its life, basically.
If the junction maximum temperature is the same, then we can expect a lower lifetime.
Okay, yeah, thank you.
Yes? The microphone comes there. Yeah.
I like this presentation because we always, when we do power cycling tests with these double cycling cooled modules, it is very, very complicated.
Yeah.
I can confirm that we do not get the results that we expect for the different technology. And you give some more further.
Thanks.
Yeah. Okay. I think we thank Said for an interesting presentation.
Thank you.
Okay. Now it's time for Khisra Abbas from KTH to talk about zero voltage switch silicon carbide MOSFET inverters for electric vehicle drives.
Hello everyone, good afternoon. So my topic of discussion is zero voltage switching silicon carbide MOSFET inverter for EV drive system. The outline of my talk includes the motivation behind this project, objectives of this project, proposed source switch three-phase inverter, results and discussion, conclusion, and at the end talk about the future work. So first of all, the motivation behind this project includes that this is the normal hard switch three-phase inverter, including the battery pack, semiconductor devices, PMSM. And then if we consider the losses in this hard switch inverter, then we see that during turning on and turning off, we are getting the switching losses as well as conduction losses. This converter is already very highly efficient, but we have a margin. To improve the efficiency of this inverter by decreasing the switching losses as well as conduction losses. And then because of these losses, we need to have some cooling system in order to cool down the semiconductor devices, and this will increase this will reduce the power density or compactness of the inverter. So there is a chance to improve the power density of this inverter. Or the second one is that because of these losses, we have the limitation on the switching frequency, and then we need to compromise on the size of DC link capacitor. So keeping these two things in mind, then we can have a margin to improve the power density as well as the compactness of this inverter. The third motivation behind this project is that these are the phase voltages and the line voltages from a hard switch three-phase inverter. Here you can see that the sharp edges of the voltages. This will create the problem for the motor, like creating the bearing motor windings and the motor bearings, and it will damage them. So it will reduce the lifespan of the motor. And the second one is that because of these sharp edges, we have the DV, high dV over dt and di over dt, and it will increase the EMI issues related to this one. And these both reduces the reliability of the inverter as well. So keeping all these motivation behind this project, we designed some objectives to increase all these factors much better, a little bit more this one. So the objective of this one, we want to increase the efficiency of the inverter by reducing the switching losses for using the soft switching techniques such as the zero voltage switching. And first we will use the semiconductor devices, silicon carbide or gallium nitride. And then we can reduce the conduction losses. I will discuss it later how to reduce the conduction losses in case of soft switching. And this will increase the efficiency of the inverter, and highly efficient inverter will increase the driving range of the EVD. So this is the benefit of this one. And if you talk about the power density, then we can increase the switching frequency because we are getting less losses due to the switching action or zero voltage switching. Then, and we can also reduce the size of the DC link capacitors. So we are also reducing the thermal management because the losses are lower. So we don't need so much thermal management requirement for this one. But for this source switching, we need to include a low pass LC filter. And then this filter we will try to minimize in volume as well as losses. So the overall inverter can give us the lower losses as compared to the hard switch inverter. So the third one is the reliability, sorry, because of the less thermal management. We can operate it because of the lower losses, because of the lower thermal management, the reliability will increase, as well as due to the lower losses, we can operate the inverter and the motor at lower temperatures and lower temperature swings, and lower dV over dt and higher reliability of the motor as we can get it here. And this will also reduce the EMI issues because we are getting the sinusoidal output voltage and current. So here is the proposed soft switch 3-phase inverter, in which I will discuss about the circuit topology, operational dynamics, autonomous gate drivers, and the LC low pass filter, which we have implemented in this design here. The circuit topology is here. Here, because we have introduced the soft switching, so we need to have for turn off on losses. In order to reduce the turn on losses or ZVS at turn on, we need to add. Sorry, this is not alpha. We need to add the filter inductor, so it can provide the requirement of bidirectional current, which can by using the bidirectional current, we can get the ZVS at high side switch as well as on the low side switch. So this inductor is necessary for the turn on ZVS, and then for the turn off ZVS, we need to include the snubber capacitance across each MOSFET because there are higher order of harmonics are also there, so we need to add the filter capacitor here. And the third distinguish is that we have the start point of this filter capacitor is connected to the midpoint of the DC link bus. This it will provide a low path impedance for the harmonics which are coming to these filter capacitors and going back to that one, and it will save the motor windings and bearings of this motor as well. So for the zero voltage switching, what we are doing that we are using the inductor current, and this inductor current discharge the output capacitance, and then the diode starts conducting, and this is the right moment to turn on the MOSFET at zero voltage. So if you see that here, that this is the VDS, and in normal hard switch converter, when we turn on the MOSFET, the output capacitance, the energy in the output capacitance discharging into the channel of the MOSFET. But in case of soft switch converter, zero voltage switching, we are discharging this capacitor already, and then we turn on the MOSFET. So in order to get the turn on ZVS. And for the turn off ZVS, I have already told that we need to have the bidirectional current, the positive peak as well as the negative peak of the inductor current. Operational dynamics. So in order to understand how the ZVS is achieved, and we have considered the single phase half bridge inverter. So this is the single phase half bridge inverter, and this is the filter inductor current. The first we have distinguished it one switching cycle we have divided into 8 modes depending on the direction of inductor current as well as the associated switching devices conducting at that moment. So we will start with mode 1 when the S1 is conducting a positive inductor current. So this is the amount of filter inductor current which is passing from the S1 switch. Now we want to turn on switch at ZVS. We will discuss later how we can achieve turn off or turn on ZVS from the driver. Now we want to turn off ZVS S2 switch. The S1 switch is already turned off. So this is the moment. If you see here, the DB1, this is the blanking time for this one. And then you can see that the half of the inductor current will going into charging of the capacitance across C1 equal to VDC, and half of the inductor current will flow to the discharge C2 equal to 0. When C2 is equal to 0, then the diode starts conducting, and this is the mode 3 when diode is conducting the positive inductor current. So this is the right moment. So this is the right moment to turn on the switch at 0 voltage. Autonomous gate driver, which I will discuss it later, it will turn on the MOSFET at this moment at 0 voltage, and this is the moment that S2 is conducting the positive, the highlighted S2 area is conducting the positive inductor current. And when now we want to turn off the switch, S2 switch. So we want to turn off the this is the positive S1, S2 is conducting the positive inductor current, and when inductor current crosses this it's 0, then it changes its direction, and the negative current, the S2 is conducting the negative inductor current. After that one, we want to turn off the S2 switch at 0 voltage, and then this is the time, again the blanking time here, that the filter inductor current will charge up C2 equal to VDC and C1 equal to 0 in order to turn on S1 at 0 voltage. Here you can see that the blanking time duration is less when the current is positive, and is a little bit more when the inductor current is negative or small in quantity. So this is the right moment to turn on this is the when the voltage across C1 switch is equal to 0, D1 starts conducting, and this is the right moment to turn on the switch at 0 voltage. So this is the moment when S1 is conducting a negative current, and after that one, the 0 crossing, the S1 starts conducting the positive inductor current. Now I want to talk about how we can generate the VGS signal, that how we do know that this is the right moment to turn on the MOSFET, the switch at 0 voltage. So we have designed this autonomous gate driver for this one. This is the novelty of this work, that we have designed this autonomous gate driver, in which when the voltage across the switch is less than 0, this is then we have implemented the high-speed comparator. This is the right moment to generate the turn-on signal by the autonomous gate drivers. And then for the turn-off signal, we have implemented shunt resistor to measure the current across the switch. And then when the current across the switch is greater than the reference value of the current, then the turn-off signal is created by the autonomous gate drivers. So the same for the lower side switches, switch. Now the question arises, how do we know that this is the right moment for the reference current? For the generation of reference current, here you can see that this is the PSM motor, and this is the measured speed, and we have the desired speed. There is a speed error, and then speed controller will generate the reference torque based on the speed error using the constant A, and the quadrature current components are there. After that one, the inverse spark transformation and the inverse Clark transformation, we are getting the reference value of the three-phase inverter. So I have here shown that how we can get the positive reference value for the high side switch and for the negative reference value for the low side switch by using this delta configuration. Now the question arises for the So now I want to discuss about the LC low pass filter, how we can choose the value of this one. For the filter inductance, if you see that this is the single phase half bridge inverter. Here, this is the filter inductor. This current is like this. The limit of this current is controlled by the reference current, which I have just discussed about right now. And after that one, when the inductor current is sinusoidal, the sinusoidal part is going into the motor, and all the high frequency components are going back from this capacitor to the DC side. So this is the filter inductance value calculation. Here we have used the input voltage, the output voltage, and this is the peak-to-peak inductor current. This is the peak-to-peak inductor current. Average current is the sinusoidal, and we have multiplied with the constant K, and when we need to include the switching frequency of that one. So this peak-to-peak current is like calculated from this one, and for this particular case, we are using this equation to calculate the filter inductance one. One thing I want to discuss here, that the turn-on signal is controlled by the autonomous gate driver. It's not in our control. Whenever the voltage across the switch is less than 0, the autonomous gate driver just detect that voltage is less than 0 and turn on the switch. So it means that we are not going to control the turn-on signal. We are just controlling the turn-off signal for the switch, and then that's why we are not controlling the switching frequency or the duty cycle of this inverter. This might be a drawback for this one. So this is the filter capacitance, how to calculate the filter capacitance. The filter capacitance value is calculated based on the how much percentage of the ripple we want to have on the output filter or output capacitor, output voltage. So this is the formula we have used to calculate that one. Now the results and discussion. So for this one, we have used LTSpice simulation software. These are the model parameters. For that one, we have used SiC MOSFET. RDS on is, sorry, this is not working. So the RDS on is like 16 milliamp ohm. And then we have used the, so this is for the 10 kilowatt, but this inverter works very well. Even 100 kilowatt, 1 megawatt is up to that one. So here we have designed the motor parameters by using the RL load equivalent to PMS motor. So now we want to check the operation of AGD. Here you can see the blue one. The blue one is the VDS, and where we see that when the VDS is less than 0, the autonomous gate driver will generate the turn on signal. And this green one is the switch current, and when this RDS, the brown one is the reference value of the current. When the switch current is greater than the RF reference current, the autonomous gate driver will generate the turn off signal. So these turn off signal and turn off signal are given to the RS latch to generate the required VGS. So this is the operation of autonomous gate driver. And the next is like we want to check that either we are getting the appropriate blanking time to discharge the output capacitance. And then here you can see that when the filter inductor current is high, we need smaller blanking time. And if the filter inductor current is small in magnitude, then we need more blanking time to discharge the output capacitance, and it will take more time. Here we can see that this is the filter inductor current, sinusoidal. One switching cycle is in triangular form, but the whole is as sinusoidal form. Here by changing the positive reference current and the negative reference current, we can change the average value of the output current. Now we want to check the turn on ZVS and the turn off ZVS. Here you can see that this is the VDS across the switch. This is the turn on signal, and this is the switch current. When the VDS is less than 0, this is the right moment when the autonomous gate driver will generate the turn on signal. Here is just the 4 nanosecond propagation delay of the comparator. And the third one, if you calculate the switching losses, turn on energy losses for this one switching cycle, you can see that it's like almost constant. It means that the autonomous gate driver makes sure to have the discharge, the output capacitance before turning on the MOSFET. So they are not, we are not getting any switching turn on losses. So it means that we are getting 0 voltage switching. And if we talk about the turn off ZVS, then I have divided one cycle into 10 different points. And if you can see that the turn off energy losses are different, it depends on this value of the snubber capacitance as well as the amount of current in the output current which we want to have. If I draw a graph on this one, then you can see. If you see the graph of this one, when the value of the current is high, we are getting the higher the turn-off losses as compared to when the amount of current is lower. So how we can decide the value of the snubber capacitance for the turn-off ZVS? If we choose the large value of the snubber capacitance and we have the low current, then it will take more time to commutate. And if we choose the smaller value of the snubber capacitance, then it will not give us the beneficial of the 0 voltage switching for turn-off. So if we consider the DC to DC converter, then we have a constant current value and we can choose one optimum value of the snubber capacitance to achieve high efficiency in terms of reducing the turn-off losses. And here we can see the DC to DC converter for using different value of snubber capacitance. Here you can see that 10 nanofarad we have reduced tremendously turn-off 0 voltage switching. And for the DC to AC converter, because the current is variable sinusoidal, so it's very difficult to choose one optimum value of the snubber capacitance. And these are the conduction losses. If we talk, how can we reduce the conduction losses? By increasing the die area. And if you see, this is the graph for a hard switch converter, that if we increase If we increase the die area, then the switching losses will increase, but the conduction losses will decrease. But this is for the case of hard switch inverter. In case of soft switch inverter, we are not getting this extra snubber. The capacitance will not affect the turn on ZVS. So we can use this snubber capacitance to implement in this one. To reduce the conduction losses. And because of the high die area, we have high capability to increase the cooling capability of this MOSFET, and we can also use this extra snubber capacitance as an effective snubber capacitance close to the MOSFET. Another approach is to use the parallel connection of several silicon carbide MOSFET. And if we talk about the power loss breakdown of the inverter, then we can see that the conduction losses are high because the high ripple in the inductor current, and then the switching losses comes mainly from the turn off losses. And if we see the power efficiency graph for the 10 kilowatt, then we can see that at low power the efficiency is high. This is because at low power we are reducing the size of the reference current, and then the ripple in the inductor current is low, and we are getting less losses of the conduction losses. Now we want to talk about the sinusoidal output voltage waveform. The left one is for the hard switch inverter. Here you have seen the phase voltage currents waveforms for the hard switch inverter, and here you can see that from this approach we have reduced the ripple in this one, and then all the sinusoidal output voltage waveforms and current waveforms. If we talk about the FFT of this one, then we can see that here in the left we have the FFT of the hard switch converter, and if you see that we have reduced a tremendous harmonics in that one, we just zoom in this area, and then it's like in millivolt or microvolt as compared to the this one. And if we just check the THT of this one, then we have zero. This is the phase current, almost similar. This is the pole voltage that we have reduced it very high, and then line voltage THD is reduced tremendously. So we have successfully designed and implement AGDs for TCM-based ZVS 2-level 3-phase inverter. We have achieved turn-on ZVS throughout the line cycle. Turn-off ZVS depends on the value of the snubber capacitance as well as the amount of phase current. Inverter efficiency exceeds 99%, excluding the filter inductor losses. And because we are getting the sinusoidal output current and voltage waveforms with minimum harmonic distortion, and it will increase the reliability and the effectiveness of this one. Because the sinusoidal output voltage and current waveforms, we have reduced the conductive and radiated EMI, and we have also increased we can say that we can increase the power density because we have reduced the cooling system, but we need to implement the low size filter components, and then it also increased the high reliability of the motor as well as inverter. So the future work is like we are working on the filter design as well on the AGDs, and these are all publications built on this one. Questions, answer.
So thank you very much. I'm sorry to say we don't have time for questions now, and we're going to have a short break now, and after that we'll start with the next session about material development, and this will start 17:30. Thank you very much.
Okay, hi everyone. So it's time for the next session to start. Ask everyone to kindly have a seat. And I invite the speaker, Jimmy Thornberg from ST Microelectronics will present crystal growth, characterization and defects in 200 millimeter silicon carbide wafers. Yeah.
Well, yes. So mouthful on that title. So, good afternoon, everyone. It's really nice to be here and a very interesting talk so far. As you can see from the title, I'm focusing more on material growth of substrates. So all of these devices is fairly new to me. So I'm Mimi Thunberg, as presented, and I finished my PhD in Linköping University 3 years ago, focusing on material science, dissertation being on hard coatings and supercapacitor materials. And I joined 2 years ago as an R&D engineer in Norrköping. That's the R&D facility for substrates, where I focus on crystal growth metrology and data analytical software development. Right, so outline. I will talk very briefly about the applications and properties because I think it's I think everyone here knows a little bit about applications of silicon carbide. So it's a bit redundant. And then I will follow up with some crystal growth with PVT, a crash course in how you grow crystals, silicon carbide crystals. And then some quality assessments of how we can verify the quality of the crystals, and then some ongoing work. Right, so this slide is very redundant. I feel that you've seen a version of this soon 15 times today. I don't think I have to convince anyone that silicon carbide is good, and that gallium nitride is also on the rise, become very good. And the applications, you probably know this better than me since you actually work in device and packaging. It's a very interesting material. Before I started work with ST Microelectronics, the only substrate I used was sapphire and manganese oxide. So for me, it was completely new to work with this. Right, and as my dear colleague Simon probably already touched a bit on, in ST, we focus a lot on vertical integration. And I think this is more and more getting traction because of you never know when the next pandemic is going to happen or when a boat is going to get stuck in a canal again. So it's good if you do as much as possible in-house because then you don't have to rely on outside sources. And there's also a lot of importance to be able to do reverse engineering when you run into problems. And if you work in industry, you know the nightmare of doing reverse engineering on a material that comes from an external supplier. Because the only thing you will get is a certificate of assurance or a MIU or material, I forgot the name of it. So it's really hard. So you want to keep it, it's very nice to have it very internally. So what we do in Norrköping, we fabricate these crystals. We do a lot of R&D on them. We try and make them better, reduce the defectivity. And after the acquisition of Norrköping, which happened 2019, I believe, ST wanted to scale up this and get into the substrate business. So what we're doing here, we are testing a lot of processes, and then we're upscaling it and porting it to Catania in the VSiC facility. So we have a mini production line in Norrköping, not even remotely close to the one in Catania, but enough to be able to test all the systems, all the softwares and all the process development things. So it's like 50-50 R&D and production line, because you need a small production line in order to test everything as well. And once we get Catania full up and running, we will focus pretty much 100% on R&D again and supply Catania with what we call seeds that you use to grow things with. In Catania, you also have this device fabs that you're well aware of. That was large well before the acquisition of Norrköping. And then we also have the packaging in China and Morocco. So what's very nice for me as an R&D engineer already here is that I can send out material in this entire flow and follow it and request any data I want. So if I have some new material that is a little bit deviating or something that I want to check, I just tell specific people I want maybe electrical EVS data, like for wafer sorting data, or maybe I go to packaging or something to check if I want to check burn-ins. So it's really nice way to close the feedback loop and not having to go through external suppliers. Yes, and even when we get Catania here up and running, I think only around 40% of the material will actually come from that facility. The rest we will still get from external suppliers. And this was quite nice. I also noticed that last year we reached top 10 in revenue market share. I think it coincides very nicely with me joining ST. And I think 2023 was when I did my first filing of patents and invention disclosures. So I don't believe in coincidences. Yes. So crystal growth, we have physical PVT. Okay. So this was not. Right. Crash course. You start with some silicon powder. The properties of this matters a lot. Grain size, stoichiometry, and everything. You put it in a graphite container that is actually composed of many parts, very sensitive. You have the roughness and everything. It plays a big role on how it's fabricated and how the condition of it. You put it in this type of furnace, and you heat it up with with magnetic fields. You can only use graphite, and you have some tack coating graphite because this is the only material that is feasible to use because it reaches operation temperature of 2000 degrees. And you did this for a very long time, 6 to 8 weeks, depending on what type of material you use. 2 weeks. I mixed up the numbers. More than 2 weeks, depending on how thick you want to grow the ingots. And what you end up with is hopefully something nice like this. Compared to, for instance, silicon, where you can grow 1 day and then you have 1 to 2 meters thickness. So it's a big difference here. So this is actually, it looks very simple, but this is why roughly 40 to 60% of the cost comes from the material. It's very difficult. And I can count on one hand how many providers today can make good 8-inch. And most of them are in this room actually today. So this is why it's very expensive. If you've seen a wafer, you probably see these two variations of it. You have a darker spot here in the middle and a darker spot here. And this was one of the first questions I asked when I started working with this material. What is this? Why do we have this? So this is a doping uniformity difference. So you know we have a dopant in the material to make it a semiconductor. So this is two different growth conditions. So you can do on-axis growth, then you mount one of these very high-quality wafers, and you grow it, and it's on axis in hexagonal structure, so it just grows like a spiral growth. Or you can do a 4-degree cut and grow it off axis. There are pros and cons in both, but the SD, we do this mainly because you reduce the doping area. So you get more, you get a better resistivity overall formation. And the facets, the crystal, they grow, it's in a hexagonal close-packed system, so they don't exactly grow in a straight line. You have a slight expansion. This is very helpful when you want to actually do expansion to different sizes. It's harder to expand, I think, gallium nitride, for instance. Yes. I don't know. This is very sensitive. Yes, and then Simona also touched a little bit. This is also very interesting. So 2022, we talked a lot. There was a press release that we're collaborating with Soitec because of the substrate being so expensive. It's very convenient to develop a process where we can use maybe one very high quality wafer several times. And while this is very relevant for silicon carbide, I think this similar process can be applied to future products. So it's worth putting a lot of effort into getting this to work. I work very closely on this material and it's looking very promising, I think. I don't know why it's every time I press. No, I don't press anything. It just happens automatically. Is it because I have an animation? No. Jesus Christ. Animation. Yeah, okay. So what can unfortunately go wrong? So here is an animation of, for instance, a polytype flip. So this is not a single wafer. It's an entire ingot, but we're taking each wafer. So you can see the 4H as amber, and then yellow, that can be 15R or... no, 15R is the green one. Yeah, no, exactly the yellow one. So this is what can happen, and this you can see very early on in the growth, in the wafering process, and then becomes completely unusable. But I think it's quite nice when you stack them up together. But if you're not... So there is a lot of other defects that is quite important. I will not talk too much about them. You can see them in the substrate, and you can also get a CVD. And this is most likely, if you work in device, this is most likely what you're more familiar with, because you work with the epitaxial, the initial epi layer. There's various techniques that you can use to analyze this. There we go. Right. So some quality assessment. One of the first things we do is resistivity check. So this is a way of us for checking. Essentially, the resistivity check is a way to check the stress in the material. It's electron mobility, essentially. So if you have a deviation in the resistivity, you have something wrong with the crystal. It might not only be the doping. And then also, if you want to put some masks on this, we want the flatness to be quite even, because that's where we have a problem with the masking. So this we can use several different tools for. I think we have mainly we use FRT in ST. But then, most importantly, what I work mostly with is defectivity. So this is very important, and it's also a bit subjective what is actually important, depending on what type of device or product you want to make. So if you work just with substrates, it's very easy to tunnel vision into making the perfect crystal. But at the end of the day, that doesn't really matter. What matters is what type of defectivity is relevant for the device you're making. So maybe stacking fault is not as relevant for one device, while it's more relevant for other device. And if you're, for instance, making smart cut wafers, then you have a completely different, you have to, in a way, consider the defects that are a little bit different as well. So it's important to understand, like, not making just a perfect crystal, but also understand like what defects are relevant. And another thing that is usually never talked about is actually the cleanliness. Like if you have a few, like too large particle on the surface, this one will act just like a killer defect. So it's also very important that the finish is good. When we have periods where we have downtime in our cleaning process, we can see it in the epi layer instantly. We see really large areas being completely unusable. So it's very sensitive to this. Okay, so some defectivity. I will not talk too much about this. I think also the next presenter from ISiCPEAW will talk a little bit about the BPD. But these are the common ones. Micropipe, it propagates in the epi layer in various forms. It doesn't necessarily have to be a micropipe or a cluster of micropipes. It can be a triangle or everything and something else. Then you have threading screw dislocations, threading edge dislocations, all type of various type of dislocations that originate mostly from the crystal or problem during the growth. So some general values. And one of the ways to define this up until now, recently, is KOH etching, some selective etching. But more and more convenient is becoming the XRT. And these values are just some general what you might expect in a product. I will talk more about some more recent, not recent, but other that is maybe not highlighted too much. We have basal-plane slip bands and we have bulk inclusions. And this is something that is not very detrimental for device. Generally, we can overcome this with good epi. But when you work with, for instance, smart cut wafers, you have to consider this because then suddenly the inclusions in the material is very important. And basal-plane slip bands is also a type of defect that is misclassified as a bar stacking fault. Okay, is it better? Okay, see if it works better. Yes, it does. Yes, okay. So what do we use to try and check these wafers? Check the defectivity. So there are several ones. The ones we use mostly is KLA Candela because it's good both for substrates and epi. But we also have Zika Laser Tech. And for epi, we also know a lot of Altair is also used. So essentially this one shines two lasers at the substrate from different angles, scattering normal and oblique laser. And then you have several detectors collecting these photons, and based on the interaction, you can determine whether or not, what type of defect it is. For instance, if you have a particle and you shine with the scattering, it will look like a bright dot, but if you have an oblique laser on it, it will look as if something casts a shadow. And from this, you can determine what type of defect it is. A lot of the new tools, and newer softwares to these tools, does this automatically in a machine learning way. So then you cycle through like 50 to 100 wafers and you point, this is a micropipe, this is a particle. And you do this enough times, and you have a machine learning that does this job for you. So you don't have to do a lot of the defining and binding yourself. But in an R&D environment, this is not really applicable in the same sense, because then you cycle new products every week, and you have new type of dopants, and you have new type of variations in the material. So you cannot really utilize machine learning in the same way. But this is the standard type of tool. This is essentially the final line of defense before shipping away, I think, for all suppliers. So you do some type of optical method to distinguish the quality of the material. And I'll show you an example of a BPSP, basal plane slip bands here, how they can look. So this is the scattering normal here, and then you have the photoluminescent channels. So you can actually see it already in the scattering normal. This is quite rare because the scattering normal, seeing this, you need some subsurface interaction. It means that there are quite significant amount of defects. Normally you see photoluminescence occurring from these type of defects, but not without epi. So this is actually without epi, so you can see this type of defects without the epitaxial layer. They look quite different in the before epitaxial layer, but they both propagate as bar stacking faults. And if you work in device, you know that bar stacking fault is a close 100% killer defect. But one you can actually see quite easily in the photoluminescence one, while the other one you can't. So this is a bit harder to distinguish, and you might misclassify it. You might not think it's relevant until you do the first epi. And then you find that you have an insane amount of bar stacking fault, and you don't know where they came from. Right. So bulk inclusions. This is something that is usually, like I mentioned, it doesn't take much focus. Honestly, it's more relevant now when we are putting a lot of effort into getting smart cut technology working. So bulk inclusions, essentially, I write bulk inclusions instead of black defects or graphite inclusions, because bulk inclusions can be anything. It doesn't need to be carbon inclusions. It can be any type of inclusion that creates a void in the material. It lands during growth, and you have growth happening around it, and then it evaporates and gets encapsulated, and you get a void. And you can have different sizes of this. Normally, in a just standard material with a normal size, you always have this in the surface. You have a promise like between 100 to 500 of this on every surface of every substrate. But EPI usually deals with this by encapsulating it, and you get a small dimple here, and then you can polish it away. But if they're large enough, they might stay, and it might not be encapsulated. This can be a problem. This is actually a very, very real problem, but in this case, we rarely let them through to device. We stop them and scrap them. But you can imagine that if you work with smart cut layer that delaminates thinner layers, like suddenly you're dealing with layers that can be as thick as the diameter of this host, and suddenly you have a new type of defectivity that you need to put attention to. And there is no good way of actually tracking this. This is something we put a lot of effort into this, because up until now there is no commercial tool that in a good way can track bulk inclusions. And here we have an example. It goes from seed up to the boule, and you see how these bulk inclusions propagate. Now, if you take this the last one, and you were to make like a smart cut wafer of it, you will see a lot of untransferable area because you have so much bulk inclusions. So this is something that we put a lot of effort into understanding. Now, this is more conventional ones that you've probably seen before. Close to the edge, we normally have a high cluster of all type of defects. We have bumps, we have triangles, we have dimps, and this is because we have a lot more strain closer to the edge. But then you have the conventional triangles that show up. We have some pit triangles and buried triangles and bar stacking faults. All of them most likely going to cause some type of error. Right, and then another toy I got beginning of this year because I wanted to expand a way of actually collecting data and understanding the defects a little bit. It's a 3D optical profiler. It's essentially a Formula 1 call of a light optical microscope. It uses interferometry. So we wanted to get a way to get good roughness and good approximation of the surface. And for this, AFM is not really good because it has a limitation in step height and it's very local. And similarly, a profilometer is essentially just a line scan. So this tool has a really wide field of view, and we can get really detailed data. We can get roughness down to 5 angstrom, and we can retain a field of view of several microns in this case. So this is a micropipe cluster that we can observe. This is a triangle, and then we have some other nice artifacts that we can see coming from, instance, the CMP. And this is interface between a poly and a mono in a smart cut type wafers. A particle has landed on the surface before bonding, and what you end up with when you polish is that you get some preferential polishing that leaves a hole in the entire monolayer. Right, okay, so I'm soon done. This is another example how this type of tool can be really good at measuring actually depth. With this tool, we can look at triangles and other epi defects, and we can determine whether or not they originate from the substrate or during the growth process, and when during the growth process. And from this, we can interpolate what the problem can be. So it's a really powerful tool. I really like it. We have already in 4 months been able to see things we've never seen before, and especially not being able to visualize. Okay. And really quick, so this is another tool that we are putting a lot of effort. It's electrical characterization for surface charging. It puts a corona-based charge on the surface and then it sweeps it. Last year in ISiCPEAW, I presented a correlation study between this type of tool and the photoluminescence tool to see an overlap. We did this on 25 200 millimeter wafers and found a really good correlation. So it's published now, or very soon, I think, whenever they want to release this. And then what I'm going to present this year in ISiCPEAW, if I can get to the last slide. There, okay. So it's a continuation of this study. So quite interesting. So in this case, we're overlapping the water reduction sites from this corona-based tool with photoluminescence and then also electrical wafer sorting. So this is a good example of a vertical integration where we go from the very bare substrate to electrical wafer sorting. And this study, we're writing it as I speak. This was the same wafers that we released last year. So we have 40,000 unique devices that we're doing some normalization and data analytical study on. We already found that things that cannot be found with the conventional photoluminescence scanning methods, we can find looking at this using corona-based dosage on the surface, looking for depletion zones. For instance, we found that a lot of gate oxide failures are more related to charge trapping and point defects that we can find in this one, but not with the conventional photoluminescence. So we have a good complement here. In many ways, this is actually more superior. Right, so the summary. So it's widely accepted, I don't need to tell you that. Basic sensitivity, well understood. A lot of work that we do actually is correlating various tools and able to see patterns that is not necessarily seen by one tool. And horizontal integration is something that we work a lot with in ST, from substrate to device to packaging. And it's in the early stage, but I feel that already it takes me no more than a few hours to get data of things that are sent into the front line like half a year ago. So it goes very quick. And essentially improved pre-science is, I think, the most powerful cost reductor in this case. If we can determine already on a substrate level what type of product we want to make of this substrate, we can save a lot of money diverging it to the correct cause. And this we need good models that we develop in-house. Yes, so that's what was it. Sorry for going 3 minutes over. Yeah.
Thank you very much. Unfortunately, we don't have time for questions. So I will invite the next speaker, Johan Ekman from Kiesel.
I have some products that if you want to look at, I have some ingots, 8-inch ingot and wafers after the break, if you want to come and check.
Okay. Thank you. Very interesting talk. The next speaker is Johan Ekman, who will present BPD-free 4A silicon carbide 6-inch and 8-inch substrates grown by the SCAPE process. Welcome.
Okay, I'm Johan Ekman. I'm founder and CEO of ISiCPEAW in Stockholm AB. We have developed a new technique for growth of silicon carbide substrates. And we took out on Thursday last week the latest generation of materials. We call it 000. It's not exactly 000, but it's nearly 000. So we have 0 micropipes, we have 0 R-type stacking faults, and we have only 5 BPDs on the entire wafer. And there are less than 30 screw dislocations per square centimeter, and the total edge pit density is 1924. So I think this is probably the best material ever made. So let's go on here. We have. It's a bit tricky with this one. Perfect. Yeah. We founded the company in 2017. We are located in the KTH Electron building in Kista. We are 16 employees. We have 9 PhDs, and we have 2 professors. Among them, Anders is here today on our team. We have developed everything with very little money compared to everyone else in the industry. And when I see all the toolings shown here by ST guys, by Jimmy, I can only get envious because we have not nearly the resources. But we instead have very clever people, so I think we have been able to achieve a lot. Here is the principle of our growth technique. Jimmy, he just showed us that he has a big bucket of powder, and then he has a seed, and then he heats up everything such that the temperature of the powder gets hotter than the temperature of the seed material, and then you start to sublime when you come to above 1600 degrees, and so the hot gases, they will stick to the cold surface, and the crystal is growing. Since the grains in the powder, they are cut along many different crystal directions, the sublimation rate in different directions is very different. So this has to the consequence that the gas mixture is changing. And they tried to equalize that by having large amounts of powder and having a long distance between the powder and the seed. However, when you do that, then you get diffusive growth instead of ballistic growth. So it is slower, so you need to have a higher temperature. When you have higher temperature, you change the silicon-carbon ratio. It gets more and more complicated to control the process. Then, when you have all these problems, you get these carbon bulk inclusions, as mentioned here before of Jimmy. So this is only some reasons, but there are many other reasons why powder growth is not ideal. So much better would be if you can have 2 plates, one polycrystalline source and a monocrystalline seed. You place them very close to each other such that you can obtain ballistic growth, because then you can grow at much lower temperature. And that would be very beneficial. However, it's difficult because then you have problems with the source material, with the polycrystalline source, because after a while it gets carbonized, and when it gets carbonized, you create defects. So you need to change the organization of the source material in order to be able to maintain a uniform gas mixture. So then you start thinking about how can I organize my source material? And this you can do by growing it with such an orientation that is highly columnar structure in the source material. And this has the big advantage that if you do like that, then silicon is moving along the columns. And when you achieve this, then the silicon-carbon ratio at the top surface of the source remains intact. And you can have a perfect silicon-carbon ratio all over the substrate. This is what we are doing. And we have patented it. So we have now 54 patents for this, filed on all relevant markets. And we have developed the growth system to produce in volume with this technique. Advantages. In our materials, we have only two types of defects left. These are the edge and the screw dislocations. All the other defects you can see with all the very nice tools of ISiCPEAW, we do not have. Our growth system is highly repeatable, so we get practically the same result every time. And every wafer is practically identical. So we do not have a certain part of the bowls with more or less defects. If we check the defects on the first seed and we compare them to the top wafer, we have practically the same defect pattern. Energy consumption with our growth system is such that we only use less than a quarter of the energy to grow our crystals compared to powder growth. We have a lower temperature and we have a much more energy efficient thermal design of our growth systems. Graphite cost is much lower, and we have now a new project, so we will improve it even more in the future. And the capital cost for one growth system is less than a quarter compared to the powder growth system. So here we have data from our latest wafers. We call it then nearly 000 because 0 micropipes, 0 bar type stacking faults. We have here 5 BPDs left on these wafers. They are all of so-called screw type. And I guess that maybe in 1 month or so we have eliminated them also completely. Average screw dislocations on this wafer is less than 50. It's less than 30 on another wafer. I talked to my CTO here just before the break. He has even better. And here on this wafer we had 80, 90 edge dislocations on the entire wafer per square centimeter. Here we have a histogram, so you can see that when it comes to the threading dislocation densities, we have in 93% of the wafer area, we have less than 3,000 edge bits, so edge dislocations or screw dislocations. Oh, we are jumping. Here we have a cross-polarization scan. So typically, if you look here on the right side, you can see in many wafers, it looks like that, small kind of hills and marks. These are strain fields from type micropipes or bigger defects. But on the left side, you have our material. You can see nothing of this at all anymore. And here, you remember you saw the slides from Jimmy here just before us. You could see the facets, big facets. These are areas where you have higher doping concentration. When you have higher doping concentration, you have lower resistivity. But in our materials here you have the lowest resistivity is 20.32 and the highest is 20.49. This is within 0.83% over an entire wafer. We developed last year the growth process for 8-inch. However, we stopped the development because we had problems with bar type stacking fault defects. And this is really very difficult to control with our growth technique. So we were struggling for like 1.5 years to get rid of these bar type stacking faults. But we figured out how it works in December last year. And now we are growing consequently every time without bar type stacking faults. So now when we have established the process for 6-inch, we are moving to 8-inch and we are now working on the 000 also for the 8-inch. I believe it will take maybe 3 months or something like that before we can get there. Production, yeah. So we have our facility. In the current facility, we have 10 growth surfaces. We can grow in parallel. We are currently building up the master library for the 6-inch. This means that we will only select the very best seed wafers, multiply them, and then we, at the point where we have so many of these highest quality wafers, we will only produce using them. And we should have so many that we can grow and grow and grow without not using our growth capacity. This will give us a certain capacity, but the plan is to increase our production capacity in a big way. So we want to build a fab for 250,000 8-inch wafers in Stockholm. And we have one investor that will take about half of the investment. And we are now evaluating 3 or 4 more, which can complement him. And they have contacted us from the Swedish government and told us that they want to support us as well. So we hope to set up a big facility in Stockholm and start producing 8-inch packs, actually. Yeah, and that was my story.
Thank you, Johan. We have time for questions. Yes, over there, Victor.
Thank you for your talk. I had a question concerning the BPDs.
Yes.
You go to your map of the BPDs.
Yes.
4 out of 5 are located at the edges of the wafer. And I remember in the early days when I was looking at...
Wait a minute.
Yeah. I think it's a previous slide. Yeah.
Here we go. Yes.
So the BPDs are located at the edges of the wafer. And I remember looking at wafers in the earlier days.
Yes.
There would be big concentration of BPDs at the edges. So I was wondering, is this a coincidence or are BPDs more prone to grow towards the edge of the wafer?
Yeah. You know, when you have PVT growth, you're growing the curved growth front. As you saw on Jimmy's images, he has a bowl shape like this. Then after growth, you can imagine that you are at 2,000 or 2,300 degrees or so. And then you start reducing the temperature. And the bowl contracts like cylindrical. Mm-hmm. So it contracts with an angle relative to the direction of the growth crystal planes. And in order to equalize the stress during the cooling down, the crystal planes are moving relative to each other. This is the formation mechanism of the basal plane dislocations. When you create BPDs in this way, you create so-called mixed type BPDs or BPD2s. And they have an angle relative to the step flow direction. When you grow on top of these BPDs, they are very easily converted to TDs. But then you have another type, which is called the BPD1s, and that's the screw type. And the screw type, they are perpendicular to the step flow direction. They cannot so easily be converted like the mixed type. So in order to eliminate them, you need to move them out of the wafer you grow. So if you grow like 1 millimeter, they are moving in the step flow direction with 14 millimeters. So for this reason, it takes much longer to eliminate this screw type. The BPDs you can see in this image, they are not of the mixed type. They are all of the screw type. So it will take some time before they are completely eliminated. And that's the answer to this question.
And like you said, 95, that's a number I have. 95% of BPDs typically do not propagate into the epi as BPDs. In your case, in your material, is that the same ratio you expect, or are those BPDs going to be BPDs in the epi as well? Do you have the same conversion ratio?
I cannot tell you 100%. I think actually for... no, I should not answer. I'm not 100% sure. So I think you convert this also. But on the other hand, these are not moving like the mixed type during current stress. So I think these are much less problematic. But yeah.
Thank you.
Okay, one more. Yeah. One more question.
I understand you're right that those which don't convert are basal plane screw dislocations.
Yes.
Yes.
It's called screw type. There are edge type, mixed type, and screw type. BPD 1, 2, and 3.
How screw type dislocations split into partials? Do they?
Sorry, they are?
Can they split into partial screw type?
I don't think so.
Yeah, we can continue the discussion after. I think
yes.
In the interest of time.
Good.
Let's thank Johan again, and we move to the next presentation. Is from Anant Agarwal, who could not come here. I think it will be a recorded presentation, right? The title of the presentation is Effective Screening Methods for Silicon Carbide Power MOSFETs to Achieve Less than 10 ppm failure rates.
Hello, everyone. I'm Anant Agarwal. Some of you may know me. I am professor at the Ohio State University in Columbus, USA. Before this, I was in Department of Energy. I'm known for creating Power America and associating SCAPE with Power America. And before that, I worked for Wolfspeed for about 14 years in the capacity of R&D director. So with that short introduction, let me start today's talk. Today, I would like to focus on effective screening methods for silicon carbide power MOSFETs to achieve less than 10 ppm failure rates. This is work in progress, so I'll show you what I have. There are four main challenges for silicon carbide in EV inverters. Number one, silicon carbide surface defects result in 2 to 3% failure of devices in EV inverters. Two main failure mechanisms. One is gate oxide failures due to surface defects. The second is drain source failures under high drain voltage due to bulk defects. So one of the consequences of drain source failures is we should not use 1.2 kV devices for 900 volt bus. We should probably use 1.5 kV devices. Number three, there is a shoot-through failure in EV inverters due to very short 2 to 4 microsecond short circuit withstand time. And therefore, we really need to screen against these three different failure modes. Today, we will focus on the gate oxide failures and screening methods. So the fourth challenge is aggressive screening of incoming power modules is needed to reduce failure rates from 2 to 3% to 2 to 3 ppm. Gate oxide failures can be associated with surface defects, and here you see the famous Princess and the Pea problem. This is a defect on the surface of the silicon carbide that makes the Princess very uncomfortable. This was pointed by Infineon, and I think this is the main problem. So when you look at a population of silicon carbide MOSFETs, you see an intrinsic branch where this is the lifetime of the good gate oxide. And there is a tail, which is extrinsic defects due to the surface problems in the silicon carbide. And the purpose of the screening would be to remove all these extrinsic defects, as many as we can, so we can achieve high lifetime. So imagine you are an inverter manufacturer, you're receiving tens of thousands of devices every day. How do you catch all the potentially bad devices without significantly damaging the good ones? So that's the problem statement. In our lab, we actually test a lot of devices. And here is an ensemble of many devices from different manufacturers measured under different gate voltages. And you can see the variable distribution of these devices. And you can see there are a lot of outliers, such as these here, such as these here. And this means there are still lurking extrinsic failures in these devices. Now, please remember that these devices were already screened by the vendor. And even after that, these devices have some extrinsic defects. So that's why we have to screen these devices as they come into the factory. So the goal is to remove potentially defective and unreliable devices, and there are three methods you can use: high gate voltage, high temperature, and long time to do this. But the constraint is you should not hurt the good devices. And that means we should not change the threshold voltage by more than 5%, and we should not change the lifetime of good devices by more than 5%. I would say again that the current screening methods employed by vendors are somewhat inadequate to catch all the extrinsic defects. There are two types of devices in the market. Planar MOSFETs, as you see on the left, and trench MOSFETs, as you see on the right. Planar MOSFETs have a thin gate oxide of about 40 nanometers. In fact, some vendors have gone below 40 nanometers. And you can see this with the red wiggly line, that is all the area that is exposed to surface defects. And the gate oxide would be prone to failure if the defects are present in this area. The trench MOSFET has a thicker gate oxide and the less exposed to the surface defects, as you see with these red wiggly lines. Now, of course, the trench sidewall has to be very smooth and the bottom should be rounded to avoid any other kind of defects. So I can say that trench MOSFETs are less susceptible to surface defects just by the very design. They may have other problems, but with respect to the gate oxide issues, they are much better, basically because they also have a thicker gate oxide. So we did determination of intrinsic lifetime by doing time-dependent dielectric measurements. And here you see vendors labeled as R and K. You have a much higher lifetime compared to planar vendors E and C. And we are generally going to operate at 5 megavolt per centimeter. And you can see that they may have enough lifetime, but remember, this is a 63% lifetime. This is not the 2 or 3 ppm lifetime. So having more margin in trench devices comes from the thicker gate oxide, which is a good thing. So here is our screening method. We basically start with initial devices at room temperature. This could be on a wafer, or this could be on packaged devices. We start by measuring the initial threshold voltage. We heat up the device at 150 degrees C. We apply the screening pulse, which could be short pulse for wafer level screen or long pulse for burn-in, for a given amount of time. And then we cool down the device to 27 degrees C. And then we wait for 48 hours and measure the threshold voltage again. So the threshold voltage at the end, which is listed here as V threshold post, minus the initial threshold voltage listed here as V threshold pre, is the change in threshold voltage, which we need to reduce to 5% or less. So we took planar MOSFETs and we applied different gate voltages in the green here, which correspond to these electric fields in the gate oxide in black. And we measured we applied 100 millisecond screening pulse, and we applied 1 second screening pulse. And you can see that the 100-second screening pulse, the threshold starts going negative at around 9 megavolt per centimeter, and that's because of the impact ionization of holes or the anode hole injection. Whereas if we go longer for 1 second, threshold shift stays within 5%. If we do the same thing on trench MOSFETs, you can see both 100 millisecond and 1 second times the threshold voltage starts going negative at around 8 megavolt per centimeter. But I want to point out that we can screen these devices up to 54.6 volts on the gate, or compared to planar, which I can only screen up to 41.7 volts on the gate. So higher gate voltage screening in trench devices would remove a lot more extrinsic defects. That's the assumption. And the next thing is lifetime. So on the left, we used silicon carbide planar MOSFETs, and we did time-dependent dielectric breakdown on screened and unscreened devices. So the blue diamonds show you the unscreened devices, and you can see we aggressively screen them for 10 megavolt per centimeter for 100 milliseconds and 1 second. And for both of these periods, we don't significantly change the lifetime. But if we go for 3 minutes, the lifetime is drastically reduced. And same thing we see here for trench MOSFETs. For 3 minutes, we significantly reduce the lifetime, but up to 1 second, we are okay. Again, this is done at 10 megavolt per centimeter, and I will remind you that 10 megavolt per centimeter means higher gate voltage in trench devices compared to the planar devices. And this is a burn-in example where we went for 10 hours at 8 megavolt per centimeter. The black dots are unscreened devices. The orange dots are screen devices or burn-in devices. And we see that we don't significantly change the lifetime. And this is a planar device, vendor E. All right, so talking about the pulse burn-in, the DC burn-in for 10 hours causes a lot of threshold voltage shift. So we invented this pulse burn-in where we go from positive voltage to negative 5 volts to positive voltage and back down again. Our pulse period is 1 second and duty ratio is 50%. And now by doing this, every time we reset the devices and therefore reduce the threshold voltage shift, and by doing this, you can see that the black dots for the planar MOSFET show you DC burn-in results. On the y-axis, we are plotting the threshold voltage shift. And on the x-axis, we are plotting the gate voltages that were applied and the corresponding gate oxide field. You can see by doing the pulse method, which is the stars in green, we can reduce the threshold voltage significantly. And the same thing applies to trench MOSFETs. We can reduce the threshold voltage shift significantly by doing the pulse burn-in. And now another dial you have is the duty ratio. We can tailor that for individual vendors. Another thing we discovered, which can be very useful, is when we measure the oxide failure time by TDDB, and we measure the initial gate leakage current in these devices, they're correlated. So higher gate leakage current means shorter failure time. And these measurements were done on planar devices at 41 volts, gate voltage at 150 degrees C. And this clearly indicates that we don't have to really screen by applying gate voltages for a long time. We can simply look at the initial gate leakage current and set a threshold of gate leakage current and screen it that way. And the correlation is actually very strong. And the correlation also holds for power modules. So these are 400 amp power modules built with planar devices, and they were screened at different voltages. And you can see that time to breakdown on the vertical axis versus gate current on the horizontal axis. You can see there's a same correlation of failure time versus the gate current in the power modules. So with that, I would just summarize by saying that it is absolutely necessary to screen incoming silicon carbide power modules against gate oxide defects to reduce the failure rates from 2 to 3% to 2 to 3 ppm, which is required by the EV industry. We are developing on-wafer screen and burn-in techniques suitable for different vendors. Obviously, we have to dial them for different vendors. So with that, thank you very much, and really appreciate your time and listening to me. Thank you.
Okay, I think you can email questions to Professor Agarwal. Our next speaker will be Professor Josef Lutz from Chemnitz University. And the title of his talk is Reliability Testing of Silicon Carbide Power Semiconductor Devices Respecting Package Die Interactions.
Now, hello, the technique is working. You can hear me? So I start. This presentation is from our team in Chemnitz. The new team leader is Professor Thomas Basler, and I'm now his staff member. And I'm happy to, since he has no time, I have to replace him. We have a long time of experience. We started with reliability research already in about 2002. So we have about 22 years, and in the moment, about 15 PhDs and 2 postdocs are working on topics of device ruggedness and reliability. Now, this is the outline of my talk. I will first start with the gate, and then with the threshold voltage problematic, and then the power cycling tests considering the interaction of different failure mechanisms. Let's start with the gate oxide reliability. Due to the talk of Professor Agarwal, I must not say much more. He has shown the same graph as I have shown you on the, oh, it's not visible, but you see on the right bottom side, it's the same graph as he has already shown. Just one difference. I have here now not plotted the time. We have increased the gate voltage stepwise with time. And so we can get a dependency on the gate voltage, and we can finish the test earlier. And we expect that we can now distinguish between the intrinsic branch and the extrinsic branch, and the extrinsics are the problem in the application. We go on and just showing some results from which we published first. That means we have here 3 manufacturers. You see 1, 2, and 3. You see there is a strong difference. 3 shows intrinsic branch and extrinsic branch, also visible for manufacturer 2, and not really visible for manufacturer 1. For manufacturer 3, you see the results on top. It is already a little bit comparable, manufacturer 3, with known as with IGBTs. which are known as to be reliable regarding gate oxide. So not on the same level, but approaching it. We can now look what is the tendency at the manufacturers. Why we have always silicon carbide less quality in gate oxide than in silicon device. Even it is SiO2, we have more interface states. We must now check when we want to have a good silicon carbide MOSFET, then we have here the channel resistance. And directly in the morning it was working. You can see, you can make the channel resistance lower when you make the thickness of the oxide layer lower, or you increase the used gate voltage. And this is now one contribution of the total. So you have always a trade-off between low Ron and high gate oxide reliability. So we find very different, much difference between the manufacturers. And much effort is done due to screening. And for qualification, of course, we can test a large number of devices for a long time. And we can also suggest these accelerated tests with stepwise increased gate voltage. But according also what has Professor Agarwal mentioned before, already before the device breaks, we see a modification in the threshold voltage. These results before were from 2017. These will now are results which will be published in this year at the PCIM conference. There are now several devices in test, several manufacturers, and a lot of single devices. And here you see now the different manufacturers. First, what is to be mentioned, the final breakdown is at a very different value for all the manufacturers. That means they have chosen a different gate oxide thickness. For manufacturer M1, 1.1 to 1.2, you see it is even decreased because he wanted to achieve a lower RDSN to have an advantage of the market. You see also there is almost for all, here you do not see really extrinsics for one manufacturer. But for the most manufacturers, you see the clear difference between the extrinsic failures, which are here for this one, and the intrinsic failures. And one sees also that the manufacturers have done intensive work on screening to improve the quality and to keep a distance to the gate voltage in the application. But with this test method, it is still the advantage that you can now compare who makes it, who does it in which way. Now we go more to the details. This is the threshold voltage, the other factor is of the gate. Typically, the threshold voltage shows a hysteresis. This hysteresis is due to charges in the gate oxide. You charge and discharge them. And when you start with a negative value, you measure negative voltage before you measure the threshold voltage upwards value. And when you start with a positive voltage, and then you measure the threshold voltage downwards value. And you have always this hysteresis. Now one just must know it. And meanwhile, there is a test method proposed. It is also becoming now a JEDEC standard that you always must apply this routine, negative voltage, then you measure the upwards value, positive voltage, then you measure the downwards value. It just must note that you always compare the same with the same. Otherwise, you can make a strong mistake in the evaluation of your test. So, but now, when we apply this method, we go now back again to the stress devices. And we'll see here already, this is one example of a trench MOSFET from SiC, stressed at the condition as mentioned before. And here we see Here we have the final point where the device fails and reaches the intrinsic limit. But we see already long before, we see an increase of the threshold voltage, which now goes here at this point out of the datasheet value. This threshold voltage increase is not uncritical. We see it on the right side. Here I have selected one of the devices. Look here to this 41 volts. Here we see already a modification in the switching behavior. This is now the current, this is the turn-on behavior. And here we see already that we get significant more turn-on losses. And here we have in the turn-off behavior. It is also modifying, but the turn-off losses are of less amount than the turn-on losses. You see turn-on losses increase, turn-off losses decrease. But finally, the sum of both, they are not really compensating each other. Now we can see that we have to take clearances also for the device application, but also the positive news is that it occurs already at a level far above the rated gate voltage for application. Now I go on. We have to know this, and now we have enough knowledge to discuss the power cycling problematic and the interaction. First, this is well known what is said here. Silicon carbide has different Young's modulus compared to silicon, about 3 times. And this gives now more stress at the interface. And in the consequence, we can expect 1/3 of the lifetime in a power module. This is modules with and without base plates, the same results. It holds not for discrete devices, which are molded. And there's this failure mechanism is not such important for the molded devices. But for the modules, we have really this type of failures. I do this very quick, just that you know what is power cycling. We have a load current, we heat up the device. We have in parallel flow and sense current to measure the junction voltage. We have done a calibration before, and then we read out the junction temperature. In addition, we supervise some other parameters online. This is one example for IGBT. Now for IGBT, we have also a lot of experience. We monitor 2 main parameters. This is the collector emitter voltage drop and the thermal resistance. And you see here in this case, you see the bond wire lift off and the increase of thermal resistance. Now we know the failure mechanisms, bond wire degradation and solder layer, bond wire lift off and solder layer degradation. With power cycling, we intend to evaluate the package. But now we have suddenly a silicon carbide device. Now we have more effects. First, this is now a result of diodes. Here you see the influence of the material in the same package. Silicon carbide has here now in a standard soldered module about 1/3 of the power cycling lifetime due to cracks growing from the edge towards the center. Okay, meanwhile, because of this effect, all power module manufacturers have improved technologies. So you must not have this when you go to silver sintering and to other advanced technologies, or to copper sintering, which is preferred by some Japanese manufacturers. Now for the silicon carbide MOSFET, we must now have a new test strategy. This is a shortcut that we can test in the same way as another diode. But for the MOSFET, we want to heat it up in the MOSFET mode and to use a body diode to determine the parameter. However, we need a negative gate voltage to close the channel. So our setup is this one, and here we first apply the gate voltage, then we turn on the auxiliary switch, then we have some delay, and then we have apply the negative gate voltage to sense the junction temperature. Now, what is the influence of the value of this negative gate voltage? This is now an example. Due to the junction voltage, the channel opens partially at 0 volt and small negative gate voltage. And I was just evaluating a paper, and the other reviewer was saying, no, it is a MOSFET, if the gate voltage is 0, the channel must be closed. No, this is not the case in silicon carbide, because there is a junction voltage, and the potential at the PN junction is at another value and is not at the value 0. And so we have a partially opened channel. It is already known for silicon MOSFETs. It is called body effect. It is already used that some silicon MOSFETs get soft recovery because they are partially channel opening at the same time. Now we check. This is different for different manufacturers. Here you see manufacturer A. After you need minimum -6 volts, then nothing more happens. And here manufacturer C, you need a little bit more negative voltage. And we now use this and we make now the calibration. Calibration means we monitor this voltage, and here on top at 0 volts and on bottom at -10 volts at the gate. And we see now at 0 volts, we execute then the power cycling test, and then we measure the same calibration function for the same device again. And look what we find. It has modified. At 0 volt, it modified due to the drift in the threshold voltage. You see for this manufacturer C in a positive way, for manufacturer A in a negative way. And this now will lead to strong errors in the junction temperature determination. And so you give wrong values. Therefore, we recommend that we have enough negative gate voltage. Here you see the values for all three are stable, despite a threshold voltage shift, because this now does less matter. This is just, we can now do the power cycling. Unfortunately, some manufacturers restrict the negative gate voltage, because it is known, as already presented in some presentations before, that it is negative gate voltage is more critical for reliability. But when you do power cycling, then we want to know the power cycling reliability. I have to mention another topic before I now implement the silicon carbide MOSFET to the power cycling tester. Sometimes in silicon IGBTs, we use the gate voltage for a fine-tuning of our temperature swing, because it influences the losses. But now we have to take care of silicon carbide MOSFETs. When we measure it, for example, this manufacturer C at 12 volts, it has a negative temperature coefficient. That means at the same gate voltage, the current increases. When we go to 18 volt for this manufacturer, now this is a negative temperature coefficient. For this voltage, now when we go to from 18 to high temperature, then the current decreases at the same gate voltage. So we must now, this is stabilizing, this can lead to current grounding. Now this point, we call it, when is the interface between positive and negative, this is the so-called temperature compensation point. We can determine it in different ways. Here we did it, here on the x-axis the gate source voltage, and here's the RDS on. Now we can see for manufacturer, for this manufacturer B, it is here at 13.5 volts. For C, it is at 11.5 volts. For manufacturer A, which is not displayed more, it is even at a lower voltage. Now, the operation below the temperature coefficient point leads to current grounding by physics. There will be flow more current. And now we have, this can reduce the power cycling capability drastically. We will have a presentation on this also on the PCIM conference this year, given more details, because it also depends on the conditions. But it's under minimum factor of 2. But under very short pulses, this can be even more when you go to a high power density when you want to heat up the device in a very short time. Now we see, this we have to avoid. We go to this point where we have a positive temperature coefficient. Now we give some results. Here I have results from a 6.5 kV SiC MOSFET module done with silver sintering. And you see we have module number 3. And we have not much successful modules because they are hard to get. This 6.5 kV, but it was expected in this effect, in this device, we find bipolar degradation. So we compared MOSFET mode for heating and inverse diode for heating up. So this is a long time with working as an applied voltage, applied operation in the diode mode, where we expect bipolar degradation. It was also mentioned in the morning for high voltage devices, this is much more probable than for 1.2 kV devices. We did not find the bipolar degradation. However, we find a strong shift in the threshold voltage. And this is very strong. You see, this is the usual mode, plus 15, minus 10. We see here we have an increase in the threshold voltage. And here we have operated it always with minus 10 volts. And here we have a strong decrease in the threshold voltage. On the right side is just the routines that I have displayed you before. Interestingly, we did not find the bipolar degradation. Now, of course, we must now take care and document the threshold voltage shift. We have this, to expect this always. When we have negative gate voltage, we induce positive charges and we decrease the threshold voltage. When we have positive voltage, then we have negatively charges and we increase the threshold voltage. Now it is of direct consequence to the channel resistance. And because here is the threshold voltage as a parameter. If the threshold voltage increases, then R1 is increasing. If it decreases, R1 is decreasing. And now we see it is of influence to our results. We can now check, okay, our failure criteria in the power cycling test is RDS1 increase. In IGBTs, we know this is a packaging technology. In silicon carbide, it can now have different reasons. One is the threshold voltage drift that I have shown you. Also bipolar degradation would lead to the same effect. And of course, we have the package degradation. Now you have to evaluate your test carefully to distinguish between the different factors. And our question, okay, we now know the importance of the threshold voltage. So best is to monitor it. And of course, we can monitor it online. Here we just need to modify our circuit a little bit more. We need some more switches. We have here, this is a current for the junction temperature measurement, the sense current. This is now the current source for the threshold voltage measurement. And those we switch and we apply this pattern. Here, negative voltage to measure the threshold voltage upwards value, positive voltage to measure the downwards value. And we have some time. We measure it before we turn on the device again to have always a similar temperature. That means there's a lower junction temperature in the power cycling test. And now we can implement this method. We have already some first results with the new method. That means now this is a method. It will be published just at PCIM this year. That means this must be 2024. That means here manufacturer A, this is the threshold voltage over the number of cycles. You see there is some modification. It is not very large and it is decreasing. But it can also be due to temperature. Therefore, we monitor in parallel the minimum junction temperature because the junction temperature must be known. Then we see another manufacturer. Here we have some increase, also not by a large amount. We must also compare it now. We have always a different minimum junction temperature unintentionally. And here we have manufacturer C. Here we have a quite strong increase of the threshold voltage. And it's now, we have also monitored the junction temperature. Also one hint, of course, test conditions for all the manufacturer were the same. They reached different power cycling capability, but this is not the thing what I want to focus now. I want to focus how to do it correctly and to take care on the different interactions. Now, what is the influence? Now, fortunately, we have these TO devices with 3 and 4 pins. And with the 4 pin, we have one sense pin directly on the chip. So we can now eliminate the influence of the bond wires. The bond wires are for all discrete devices, the bond wires are failure limiting. And now we can check, and when we now select a point where our lower junction temperature is more or less stable, then we see in this part develops a difference. This was a measurement as the increase of the voltage drop at the main load terminal, and this was at the sense terminal. And so you see we have some contribution, most of the load, but some of the sense for manufacturer C. The chip only is more exposed, but of course manufacturer C has much more cycles to failure. And now we can see in total failure limit is 1.5%. And so we can see, okay, we have here already in this interval 0.3% contribution of the threshold voltage shift. And we have here finally the main contribution, of course, is when we reach the limit of the bond wire failures, then we have a significant jump. Now we see now you can distinguish, can a little bit analyze the influence of the different things. Let me summarize my talk. This threshold voltage shift is typical for silicon carbide devices, and always when you stress the device, you must know that it is to expect. It is, of course, already long before the final gate breakdown. So as Professor Agarwal pointed out before, he uses already now this knowledge that he must not go to the failure limit of all devices. He sees before the threshold voltage influence. And now this threshold voltage shift can lead to strong errors in the junction temperature determination if the channel is not sufficiently blocked with a sufficient negative gate voltage. Documentation before and after test is recommended. Recalibration after power cycling test I recommend. You have done a lot of effort, so you can measure your calibration function again. This threshold voltage shift can contribute to the failure limit, may lead to a wrong statement of your packaging technology. Maybe this is not as bad as you expect. And we did not find bipolar degradation in the
tests reported by me up to now. Also in many other power cycling tests, we did not find it. We can, however, provoke it with surge current test or at high current density in another mode of application. But in the recent time, we did not find this at currents in the range below 2 times rated current for all manufacturers. But there are still differences between the different manufacturers. But this is now not the aim of my talk. The aim of my talk is to give you some arguments how to execute reliability tests. Thank you. Oh, I like questions. Thank you.
I just want to say last announcement. Please stay for very short session before we go to the garden and to the dinner, because we have announcement of this year's rewards for young scientists, and we were talking about the shortage of the educated personnel for power electronics job, and so we try to do what we can from the center to promote that, and Per will do it. Per, please do not keep us too long, because the wine will get warm.
I understand that, and it's always the last one which is blamed for the overruns. Good. Thank you. Do you flip you flip this one? Yep, good. So, you can take the next slide. So the Wide-Bandgap Power Center decided some years ago to promote young engineers and students to work in the area of wide-bandgap power electronics, to introduce 2 annual awards. One which is Best Thesis Award and targets master thesis and bachelor thesis. And the other one is Young Professional Award, which could be industrial R&D, or it could be in the academia as PhD. And these are to be presented at SCAPE. So that's the reason why we're here. And last year, we didn't run SCAPE, so we have 2 years. So we have 4 awardees to present today. And I'm here in the role as chairman of the board of the Wide-Bandgap Power Center. And this is one of the most pleasant tasks in that role. I'm always looking forward to this one. So, let's start. So for Best Master Thesis Award, good. For 2022, we have selected Halvor Ekrén from the Norway University of Technology and Science in Trondheim to receive this one. And he has a his thesis, 4-level active gate driver for loss and slope control in SiC MOSFETs. And Halvor couldn't make it to the conference this time, so he will be represented by his supervisor for the work, Dimos Peftitis. Welcome. So,
yes, thank you.
And to you also, being a very good teacher.
Yeah, thank you very much. And is this on?
Could be. I don't know.
Halvor couldn't make it today. He's very busy at work, so I received his award on his behalf. And he would like to say thank you. And I will make sure that this will be delivered to Halvor when I'm back.
Very good.
Thank you.
Thank you. And there'll come another task for you later.
Okay.
So that was 2022 Best Thesis Award. So next, please. And Second Young Professional Award for 2022 has been selected to be given to Daniel Johannesson from KTH on the work Ultra-High Voltage Silicon Carbide Device Performance Requirements and Limitations in High Power Application. Please come.
Thank you.
Welcome. So Daniel has a poster over there, and you can discuss with him if you want to discuss the work. It's Christian and Vida carefully reading presently. Yes. So, and now we take the third one, which is Agnimitra Saha, which has been awarded for the best thesis of this year, 2023. AC gate bias stress of 4H SiC MOSFETs. And the work is done at KTH at OnSemi. Welcome. And now we need to look at your supervisor because she's taking a photo. Done. Congratulations. Thanks. And the fourth award to give out today is Young Professional Award for 2023 to Daniel Alexander Phillips, also from NTNU, Norway, with the same excellent supervisor, coming to the table. And the title of the PhD thesis is on dynamic characterization, evaluation, and control of active gate drivers for SiC power MOSFETs. So.
Yes, of course, Daniel was not able to attend SCAPE this year, so I'll make sure that he will get the award, and on he say thank you, and he really appreciates that.
Yeah, very good work.
Thank you.
Thank you. And by that, we close this award ceremony. Did I meet the time schedule?
Yes.
Thanks.